Stand outside on a clear night and look up. The stars you see, only a few thousand visible to the naked eye, are extraordinarily distant. The nearest, Proxima Centauri, is 4.24 light-years away, meaning the photons reaching your eyes left that star more than 4 years ago while traveling at 300,000 kilometers per second. Even this close distance is far beyond normal human intuition, and it represents only the smallest scale of our galactic neighborhood. The observable universe spans roughly 93 billion light-years across, defined by the distance light has been able to travel since the Big Bang. Beyond this horizon, space almost certainly continues, potentially without bound. Galaxies gather into clusters. Clusters link into superclusters, and these assemble into filamentary structures separated by vast cosmic voids. These scales are not philosophical abstractions, but quantitatively measured realities. The universe is not just large, it surpasses the limits of human cognitive comprehension. The observable universe isn't the whole universe. When astronomers talk about the observable universe, they're describing a sphere with Earth at its center. This sphere has a radius of about 46.5 billion light-years in every direction. Do the math and you get a diameter of roughly 93 billion light-years. That number itself seems impossible. After all, the universe is only 13.8 billion years old. How can we see objects 46.5 billion light-years away if light has only had 13.8 billion years to travel? The answer lies in expansion. Space itself has been stretching this entire time. A photon that left a distant galaxy 13.8 billion years ago has been traveling toward us, yes, but the galaxy it left behind has been moving away from us as space expands. By the time that ancient light reaches our telescopes, the galaxy that emitted it is now 46.5 billion light-years distant. This creates an important distinction. The observable universe is simply the region from which light has had time to reach us. It's a bubble of visibility centered on Earth, defined by the speed of light and the age of the cosmos. But nothing suggests the universe stops at this boundary. In fact, all evidence points to the universe extending far beyond what we can observe, possibly infinitely. The observable universe is like standing in the middle of an enormous ocean with a fog bank surrounding you at every horizon. You can see a certain distance, but the ocean doesn't end where your vision fails. It keeps going. The cosmic microwave background radiation, that faint glow left over from the Big Bang, marks the edge of our observable sphere. When we look at this radiation, we are seeing the universe as it was just 380,000 years after the Big Bang. At that moment, the universe cooled enough for atoms to form and light to travel freely for the first time. This ancient light has been stretched by expansion into microwave wavelengths, and it comes at us from every direction in the sky. It's the oldest thing we can see, the ultimate horizon. Beyond that wall of ancient light, the universe was opaque, filled with a hot plasma that scattered photons in every direction. We cannot see through it. Anything farther away is permanently hidden from view, not because it doesn't exist, but because there hasn't been enough time for its light to reach us. Scientists estimate the true size of the universe could be at least 250 times larger than the observable universe, though this is speculation based on models of cosmic inflation. Some theories suggest it could be infinite. If space is truly infinite, then the question, how big is the universe, has no answer in the conventional sense. Infinity is not a number. It's a concept that destroys scale. An infinite universe would contain infinite galaxies, infinite stars, infinite planets. Every possible arrangement of matter would not only exist somewhere, but would exist infinitely many times. There could be infinite copies of Earth, of you, of this moment, scattered across the infinite expanse. This isn't science fiction. This is a legitimate consequence of an infinite universe with finite matter density. But even if the universe is finite, it's unimaginably large. The observable universe alone contains an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Our own Milky Way has between 100 and 400 billion stars, and it's just one galaxy among trillions. When you start multiplying these numbers, you arrive at a figure so large it becomes meaningless to human intuition. There are more stars in the observable universe than grains of sand on all of Earth's beaches. That comparison gets used frequently because it's one of the few ways to make the scale even slightly relatable. But even it fails to capture the true enormity. A grain of sand is still something you can hold. A star is 1,000,000 times the volume of Earth, burning with nuclear fire. The comparison breaks down immediately. The expansion of space complicates everything further. Galaxies beyond a certain distance are moving away from us faster than the speed of light. Not because they're traveling through space that quickly. Nothing can do that, but because the space between us and them is expanding rapidly enough that the distance grows faster than light can cross it. These galaxies are beyond what's called the cosmic event horizon. We can see some of them now because we're looking at ancient light that left them billions of years ago when they were closer. But light leaving those galaxies today will never reach us. The expansion will carry them beyond our view forever. This means the observable universe is actually shrinking in terms of what will be visible to future astronomers. Trillions of years from now, if any observers still exist, they will see far fewer galaxies than we do today. Most will have been carried beyond the horizon by expansion. The shape of the universe matters too. Observations suggest the universe is flat, or very nearly so, at least as far as we can measure. This doesn't mean it's shaped like a pancake. In cosmology, flat refers to the geometry of space. A flat universe extends infinitely in all directions. A curved universe could be closed, like the surface of a sphere, finite, but without edges. Current measurements of the cosmic microwave background indicate the universe's curvature is so close to zero that it's either perfectly flat or so close to flat that we can't measure the difference. If it's truly flat, then it's almost certainly infinite. If it has even a tiny amount of curvature, it could be finite but extremely large, far larger than the observable universe. The edge of the observable universe is moving away from us at the speed of light. Every second, light from an additional 300,000 kilometers of space reaches Earth for the first time. But that doesn't mean the observable universe is growing. Because space itself is expanding, distant regions are being carried away faster than new regions are entering our view. The net effect is complex and depends on the rate of expansion, which itself is accelerating due to dark energy. Far in the future, as acceleration continues, the observable universe will contain fewer and fewer galaxies. Eventually, in hundreds of billions of years, an observer in the Milky Way would see a sky almost entirely empty, with only the nearest gravitationally bound galaxies remaining visible. The rest of the universe would have been carried beyond the horizon forever. This raises a profound question. If we can only observe a finite portion of the universe, how can we claim to know anything about what lies beyond? The answer is consistency. The laws of physics appear to be the same everywhere we look. The cosmic microwave background is remarkably uniform, with temperature variations of only 1 part in 100,000. This uniformity suggests that the universe looks roughly the same in all directions, at least on large scales. If the observable universe is a representative sample of the whole, then the regions beyond our view likely contain more of the same. More galaxies, more stars, more space. There's no reason to think the universe suddenly changes beyond the horizon. It just keeps going. But what if it doesn't keep going? What if the universe is finite? If so, what's beyond the edge? These questions rest on a misunderstanding. A finite universe doesn't need an edge. The surface of a sphere is finite, but has no boundary. You can travel in one direction forever and never reach an edge. You simply loop back to where you started. The same could be true of a finite three-dimensional universe. It could curve back on itself in a higher dimension, creating a space that is bounded but without borders. This is difficult to visualize because we're three-dimensional creatures trying to imagine a four-dimensional structure, but the mathematics works perfectly. Such a universe would be vast, but not infinite. Travel far enough in one direction and you'd eventually return to your starting point, having circumnavigated the entire cosmos. The distinction between the observable universe and the actual universe is crucial. When astronomers measure the size of the universe, they're measuring what we can see, not what exists. The true universe is almost certainly much larger, possibly infinitely so. The numbers we use, 93 billion light-years across, 2 trillion galaxies, these describe only our local cosmic neighborhood, the tiny bubble of space from which light has had time to reach us in the 13.8 billion years since the Big Bang. It's the ultimate case of not seeing the forest for the trees. We're sitting in a small clearing, surrounded by fog, with instruments that let us peer a certain distance into the mist. Beyond that, we can only speculate, guided by theory and the patterns we see in the data. The universe may go on forever, or it may not, but either way, it's bigger than we can observe, bigger than we can truly comprehend. Measuring cosmic distances beyond light years. When you hear that the Andromeda Galaxy is 2.5 million light-years away, it sounds like a specific, comprehensible measurement. It's not. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. Multiply that by 2.5 million, and you get a number so large, it's functionally meaningless to human cognition. We say the words, we write the numbers, but the actual distance is beyond imagination. To put it differently, if you could somehow travel at the speed of light, which you can't because physics forbids it, you would need 2.5 million years to reach Andromeda. Not 2.5 million years as experienced by someone on Earth, but as measured by a clock traveling with you. For observers left behind, even more time would pass due to relativistic effects. Light speed is a hard limit in our universe. Nothing with mass can reach it. Photons, which have no mass, travel at exactly 299,792 kilometers per second in a vacuum. This isn't just fast, it's the speed at which causality itself propagates. When you see a star, you're not seeing it as it exists now. You're seeing ancient light, a historical image. The star could have exploded years ago, and you wouldn't know until the light from that explosion finally arrived. The farther away an object is, the further back in time you're looking. Telescopes are time machines, not in the science fiction sense, but in a very real observational sense. The deeper we look into space, the older the universe appears. The nearest star system, Alpha Centauri, is 4.37 light-years away. The fastest spacecraft ever built, the Parker Solar Probe, reaches speeds of about 700,000 kilometers per hour relative to the Sun. At that speed, it would take over 6,500 years to reach Alpha Centauri. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object at about 23 billion kilometers from Earth. It's been traveling for over 45 years and has barely left the solar system. If it were headed toward Proxima Centauri, which it's not, it would take over 70,000 years to get there. These numbers reveal the brutal truth about interstellar travel. It's not just difficult, it's borderline impossible with current technology. Light-years are a useful unit for measuring cosmic distances, but they're still inadequate for truly vast scales. Astronomers often use parsecs instead. 1 parsec equals 3.26 light-years, or about 31 trillion kilometers. The term comes from parallax arc-second, a unit derived from the way nearby stars appear to shift position slightly as Earth orbits the Sun. For galaxy-scale distances, astronomers use kiloparsecs, thousands of parsecs, and megaparsecs, millions of parsecs. The Milky Way galaxy is about 30 kiloparsecs across. The Andromeda galaxy is 0.77 megaparsecs away. The nearest large galaxy cluster, the Virgo cluster, sits about 16.5 megaparsecs distant. At this scale, light-years become cumbersome. It's easier to talk in megaparsecs, even though the human brain finds neither unit remotely intuitive. To understand just how limiting light speed is, consider this. If you wanted to send a message to a civilization on a planet orbiting Proxima Centauri Using radio waves, which travel at light speed, it would take 4.24 years for your message to arrive. Their reply would take another 4.24 years to reach you. A simple conversation would span nearly a decade. Now extend that to galactic scales. A message to the other side of the Milky Way would take 100,000 years to arrive, assuming anyone was there to receive it. Intergalactic communication is even more absurd. A signal sent to Andromeda today wouldn't arrive for 2.5 million years. By the time a reply reached Earth, 5 million years would have passed. Any civilization trying to maintain such a correspondence would need to last millions of years without interruption, preserving the context and intent of messages across evolutionary timescales. The speed of light isn't just a practical limit on travel and communication, it's a fundamental constraint on causality. Events separated by more than the time light takes to travel between them cannot influence each other. This creates a structure to space-time, where every event has a past light cone, the set of all events that could have influenced it, and a future light cone, the set of all events it could influence. Anything outside these cones is causally disconnected. For observers on Earth, most of the universe is and always will be beyond our causal influence. We can see it, study it, and wonder about it, but we can never affect it, and it can never affect us. The light speed limit makes the universe effectively infinite from a causal standpoint, even if it's finite in size. Scale becomes even more abstract when you consider the largest structures in the universe. The Laniakea supercluster, which contains the Milky Way, spans 520 million light-years. Light from one side of Laniakea takes 520 million years to reach the other side. When dinosaurs walked the Earth, photons that are only now reaching the far edge of our supercluster were just leaving its near edge. These structures are so vast that trying to visualize them is futile. We can model them mathematically, create simulations, map their locations, but the actual physical scale is beyond human comprehension. A galaxy is large. A supercluster is incomprehensibly larger. And yet superclusters are just threads in the cosmic web, part of a larger structure that extends across the entire observable universe. The cosmic distance ladder is the method astronomers use to measure these vast scales. It starts with parallax, the apparent shift in a nearby star's position as Earth orbits the Sun. This works for stars within a few hundred light years. Beyond that, parallax angles become too small to measure accurately. Astronomers then use standard candles, objects with known intrinsic brightness, to measure greater distances. Cepheid variable stars pulse at rates directly related to their luminosity. Measure the pulse rate, and you know how bright the star actually is. Compare that to how bright it appears, and you can calculate its distance. This method works for tens of millions of light years. For even greater distances, astronomers use type Ia supernovae. These stellar explosions have remarkably consistent peak brightness, making them ideal standard candles for measuring distances to other galaxies. By observing type Ia supernovae in distant galaxies, astronomers can determine how far away those galaxies are. This method revealed one of the most shocking discoveries in cosmology. The universe's expansion is accelerating. Distant supernovae are farther away than they should be if expansion was slowing down under gravity's influence. Something is pushing space apart, and we call that something dark energy even though we have no idea what it is. This discovery came from measuring distances accurately across billions of light years, showing just how far our reach extends. But even supernovae have limits. For the most distant objects, astronomers rely on redshift. Light from distant galaxies is stretched by the expansion of space, shifting it toward longer, redder wavelengths. The amount of redshift tells us how much the universe has expanded since the light was emitted, which in turn tells us how far away the object is. The most distant galaxies we've observed have redshifts of 13 or higher, meaning their light has been traveling for over 13 billion years. We're seeing them as they were when the universe was less than 700 million years old, long before the Sun or Earth existed. These galaxies are now more than 30 billion light years away due to expansion, but we see them as they were in the ancient past, frozen in time by the finite speed of light. Every method in the cosmic distance ladder has uncertainties. Parallax errors, standard candle variations, redshift complications. All of these introduce margins of error that grow larger with distance. Measuring the size of the observable universe to within a few billion light-years is considered good accuracy given the scales involved. This is why different sources sometimes give slightly different values for cosmic distances. They're not wrong. They're working with different data sets and different assumptions. The numbers are best estimates, refined over decades of observation and calculation, but they're still estimates. The universe is so large that even our most precise measurements have built-in uncertainty factors that span millions of light-years. Galactic scale. The Milky Way expanded. Our home galaxy, the Milky Way, stretches approximately 105,700 light-years from edge to edge, though some estimates push this to 200,000 light-years if you include the outer halo and satellite galaxies. The visible disk, where most of the stars reside, is about 1,000 light-years thick near the Sun's position, though it thins out toward the edges. The Sun itself sits roughly 26,000 to 28,000 light-years from the galactic center, about halfway out along one of the spiral arms. We orbit the center of the galaxy at approximately 828,000 kilometers per hour. At this speed, it takes the Sun about 225 to 250 million years to complete one orbit. The last time we were in this position in our galactic orbit, dinosaurs were just beginning to dominate Earth. The Milky Way contains between 100 and 400 billion stars. The uncertainty in this estimate comes from the difficulty of counting stars we can't see. Most stars are small, dim red dwarfs that barely shine at all. The bright stars we notice in the night sky are actually quite rare. For every star like the Sun, there are dozens of red dwarfs too faint to see without a telescope. The galaxy's total mass is even more uncertain because most of its mass isn't in stars at all. Dark matter, an invisible substance that interacts with regular matter only through gravity, makes up about 85% of the galaxy's mass. We know it's there because the galaxy rotates too fast for the visible matter alone to hold it together. Without dark matter's extra gravitational pull, stars in the outer regions would fly off into space. The galactic center hosts a supermassive black hole called Sagittarius A*, with a mass of about 4.15 million times that of the Sun. This might sound enormous, but it's actually quite small compared to black holes in other galaxies. Some supermassive black holes weigh billions of solar masses. Sagittarius A* is relatively quiet right now, not actively consuming much matter. But over the galaxy's history, it has likely had periods of intense activity, pulling in gas and dust and radiating enormous amounts of energy. The stars near the galactic center orbit Sagittarius A* at tremendous speeds. Some complete orbits in as little as 15 years, traveling at several percent of light speed. Watching these stars over decades has allowed astronomers to measure the black hole's mass with high precision and confirm that general relativity's predictions hold even in such extreme gravitational environments. The Milky Way isn't alone. It's part of the Local Group, a collection of more than 80 galaxies spanning about 10 million light-years. The largest member is Andromeda, which is roughly 2.5 million light-years away and approaching us at about 110 kilometers per second. In approximately 4.5 billion years, Andromeda and the Milky Way will collide. This sounds catastrophic, but galaxies are mostly empty space. Stars are so far apart that actual stellar collisions will be rare. Instead, the two galaxies will pass through each other, their shapes distorted by gravity, eventually merging into a single larger galaxy. This process will take hundreds of millions of years. The Sun and Earth will likely survive the collision, though our night sky will look dramatically different, filled with new stars and disrupted spiral arms. The Milky Way has a complex structure. The main disk is where most stars live, organized into spiral arms that wind around the galactic center. These arms aren't solid structures. Stars move in and out of them as they orbit. The arms are actually density waves, regions where stars and gas clouds bunch up temporarily before spreading out again. This is why spiral arms appear bright. They contain more stars and active star-forming regions. The Sun is currently located in a minor arm called the Orion Arm, or local spur, positioned between two major arms. Our position gives us a clear view of the galaxy's structure when we look toward the center on summer nights, though interstellar dust blocks much of the visible light. Surrounding the disk is the galactic halo, a roughly spherical region containing old stars, globular clusters, and vast amounts of dark matter. Globular clusters are dense balls of hundreds of thousands of stars, all orbiting the galactic center on highly elliptical paths. These clusters are ancient, some nearly as old as the universe itself. They contain stars formed in the Milky Way's earliest days, before the disk fully developed. Studying these ancient stars gives astronomers insight into the galaxy's formation history. The halo extends far beyond the visible disk, perhaps 200,000 light-years or more, though it's so diffuse at those distances that defining an exact edge becomes arbitrary. The galaxy is home to enormous clouds of gas and dust where new stars form. The Orion Nebula, one of the nearest star-forming regions, sits about 1,350 light-years away and spans roughly 24 light-years across. Inside, dozens of new stars are being born from collapsing gas clouds, their intense radiation illuminating the surrounding material. This nebula is visible to the naked eye as a fuzzy patch in Orion's sword. What we see is a tiny fraction of the total structure. Most star-forming regions are hidden behind layers of dust that absorb visible light. Infrared telescopes can peer through this dust, revealing vast stellar nurseries scattered throughout the galactic disk. The Milky Way forms several new stars per year on average, though this rate has slowed considerably since the galaxy's early, more chaotic days. The galaxy's rotation presents a mystery. Stars in the outer regions orbit faster than they should given the amount of visible matter. If only normal matter were present, stars far from the galactic center would orbit slowly. Much like outer planets in the solar system orbit the Sun more slowly than inner planets. But galactic rotation curves stay flat, with outer stars moving just as fast as those closer to the center. This can only work if there's a massive halo of invisible matter providing additional gravitational pull. This was one of the key pieces of evidence for dark matter. Without it, the galaxy's rotation makes no sense. Either our understanding of gravity is wrong, or there's a lot of matter we can't see. Most physicists favor the dark matter explanation, though modified gravity theories haven't been completely ruled out. Travel across the Milky Way is beyond any current or near-future technology. At the speed of Voyager 1, it would take roughly 2 billion years to cross the galaxy. Even if we could somehow achieve 1% of light speed, which would require energy sources and propulsion systems far beyond anything we have, it would still take 10 million years. The galaxy is effectively uncrossable by any civilization limited to slower-than-light travel. This has implications for the Fermi paradox, the question of why we haven't detected alien civilizations despite the vast number of potentially habitable planets. One answer is simply distance. Even if intelligent life is common, the galaxy is so large and travels so slow that civilizations might rarely make contact. They could be out there, thousands or millions of light-years away, and we'd never know. The Milky Way itself is just one galaxy among trillions. It's not particularly special, a fairly typical spiral galaxy, neither especially large nor especially small. Andromeda is somewhat bigger. Other nearby galaxies are much smaller, irregular dwarf galaxies with only a few billion stars. The Magellanic Clouds, visible from the southern hemisphere, are satellite galaxies orbiting the Milky Way. The Large Magellanic Cloud contains about 30 billion stars and sits 163,000 light-years away. The Small Magellanic Cloud is smaller and farther, at 200,000 light-years. Both are being slowly torn apart by the Milky Way's gravity and will eventually be absorbed entirely, their stars added to our galaxy's collection. The universe's intergalactic emptiness. When you look at images of galaxy clusters packed with hundreds or thousands of galaxies, it's easy to forget that these structures are mostly empty space. The distance between galaxies within a cluster can be millions of light years. The spaces between clusters are even more vast, sometimes hundreds of millions of light years across. These regions, called cosmic voids, contain very few galaxies. They're not completely empty. There's still gas, dark matter, and the occasional lonely galaxy drifting through, but compared to galaxy-rich regions, voids are stunningly barren. The largest known void, the Bootes void, spans 330 million light-years and contains only around 60 galaxies, where a typical region of that size might contain thousands. Intergalactic space isn't a perfect vacuum, but it's close. The density is roughly 1 hydrogen atom per cubic meter on average, though this varies significantly depending on location. Near galaxies and in galaxy clusters, the density is higher. In voids, it drops even lower. For comparison, Earth's atmosphere at sea level contains about 10 to the power of 25 molecules per cubic meter. Even the best laboratory vacuums on Earth are denser than intergalactic space. This extreme emptiness means that a spacecraft traveling between galaxies would encounter almost nothing. No drag, no collisions, no interactions with matter. Just endless, empty darkness. This emptiness is punctuated by the intergalactic medium, a diffuse plasma of ionized hydrogen and helium left over from the Big Bang. This gas is incredibly hot, millions of degrees Kelvin in galaxy clusters, heated by shock waves and radiation from galaxies and black holes. Despite its high temperature, the gas is so thin that it radiates very little energy and is nearly invisible in optical light. X-ray telescopes can detect it, revealing vast clouds of hot plasma filling the space between galaxies in clusters. This gas contains more mass than all the stars in the cluster's galaxies combined, though it's spread out over such enormous volumes that its density remains incredibly low. The intergalactic medium also contains metals, elements heavier than hydrogen and helium, ejected from galaxies by supernovae and stellar winds. These metals, produced in the cores of massive stars, get blasted into intergalactic space when stars explode. Over billions of years, this process has enriched the intergalactic medium with small amounts of carbon, oxygen, iron, and other elements. The presence of these metals in the space between galaxies is evidence of past stellar activity and provides clues about the history of star formation and galactic evolution across cosmic time. Studying the composition of the intergalactic medium tells astronomers how galaxies and the space around them have changed over billions of years. Cosmic voids are not just empty regions, they're actively repelling galaxies. The expansion of the universe isn't uniform. Dense regions like galaxy clusters are held together by gravity and don't expand internally. But voids expand faster than average because there's not enough matter to slow the expansion. Over time, this has created a foam-like structure to the universe, with galaxies clustered along filaments and walls surrounding vast, empty regions. Voids have grown larger over time as expansion has continued, pushing galaxies away from their centers. The largest voids today are remnants of slight underdensities in the early universe that have been amplified by billions of years of expansion. Light crossing intergalactic space encounters almost nothing, which is why we can see distant galaxies at all. If space were filled with dust and gas at the densities found within galaxies, the universe would be opaque beyond a few million light-years. We'd see a crowded local region and then nothing. But the emptiness of intergalactic space allows light to travel unimpeded for billions of years. Photons emitted by a galaxy 10 billion light-years away can reach Earth without significant absorption or scattering. This transparency is crucial for cosmology. It lets us observe the ancient universe and study its evolution over time. However, intergalactic space isn't completely transparent to all wavelengths. Ultraviolet light from distant galaxies is absorbed by the intergalactic medium, a process called the Lyman alpha forest. Hydrogen atoms in intergalactic space absorb UV photons at specific wavelengths, creating a series of absorption lines in the spectra of distant quasars. By studying these absorption features, astronomers can map the distribution of hydrogen in intergalactic space and track how it has changed over cosmic history. The Lyman alpha forest provides a unique probe of the universe's structure on scales too large for direct imaging, but small enough to show the clumpy distribution of matter along the line of sight to distant objects. The emptiness also means that interactions between galaxies are relatively rare. In the vast spaces between galaxy clusters, a typical galaxy might go billions of years without encountering another galaxy closely enough to interact gravitationally. This isolation allows galaxies to evolve undisturbed, their stars forming and dying according to internal processes rather than external influences. Within clusters, the situation is different. Galaxies are close enough that interactions are common, leading to mergers, tidal stripping, and ram pressure stripping, where fast-moving galaxies lose their gas to the hot intracluster medium. These interactions shape the population of galaxies in clusters, making them systematically different from galaxies in less dense environments. Gravitational interactions can occur across these empty spaces. Although galaxies may be millions of light-years apart, their gravitational influence extends far beyond their visible boundaries. Dark matter halos around galaxies extend much farther than the visible stars, and these halos can interact even when the galaxies themselves are widely separated. Over time, small tugs from distant galaxies can alter orbits and influence the large-scale structure of the universe. This is how cosmic filaments form, long chains of galaxies connected by gravity across hundreds of millions of light-years. The space between galaxies isn't isolated. It's part of a vast gravitational network that connects all the matter in the universe. Measuring distances across intergalactic space is challenging. There are no convenient signposts, no stars to use as reference points. Astronomers rely on the galaxies themselves, using their properties as distance indicators. The brightest galaxies in clusters, for example, tend to have similar intrinsic luminosities, making them useful standard candles. Redshift provides another distance measure, though it requires converting the observed redshift into a physical distance using models of cosmic expansion. These methods have uncertainties, especially at large distances, but they've allowed astronomers to map the three-dimensional distribution of galaxies across billions of light-years. The resulting maps reveal the cosmic web's structure, a network of filaments, walls, and voids spanning the observable universe. The emptiness of intergalactic space has philosophical implications. If you were somehow transported to a point midway between galaxies in a cosmic void, far from any stars, the night sky would be almost completely black. No Milky Way stretching overhead, no bright stars, just a few faint smudges, distant galaxies too far away to appear as more than dim patches of light. You would be in a volume of space larger than the entire visible universe was when it was 1 billion years old, and yet you would see almost nothing. This emptiness is the universe's natural state. Galaxies, stars, planets, these are rare concentrations of matter in an overwhelmingly empty cosmos. We live in an unusually dense environment, a tiny island of matter in an ocean of nothingness. Galactic cities within cosmic filaments. Galaxies don't exist in isolation. They gather into groups and clusters, held together by gravity. Our local group is a small example, containing the Milky Way, Andromeda, Triangulum, and dozens of smaller galaxies. But this is nothing compared to rich galaxy clusters like the Virgo cluster, which contains over 1,500 galaxies within a region roughly 15 million light-years across. The Coma cluster, even farther away at about 336 million light-years, contains over 1,000 large galaxies and possibly tens of thousands of smaller ones. These clusters are the largest gravitationally bound structures in the universe. Everything else, superclusters, filaments, the cosmic web, is held together by expansion and large-scale structure, not by gravity alone. Inside a cluster, galaxies move at tremendous speeds, often thousands of kilometers per second. In the Coma cluster, galaxies zip around at an average speed of about 1,000 kilometers per second. Despite these high velocities, the cluster remains bound because the combined gravitational pull of all the galaxies, and especially the dark matter, keeps everything together. The hot intracluster gas also plays a role, adding mass and filling the space between galaxies. This gas is heated to tens of millions of degrees by the gravitational energy released as matter falls into the cluster. It radiates X-rays, making clusters visible to space-based X-ray telescopes like Chandra and XMM Newton. The mass distribution in galaxy clusters is surprising. Visible galaxies make up only about 2% of the total mass. The hot intracluster gas accounts for roughly 15%. The remaining 83% is dark matter, invisible and detectable only through its gravitational effects. We know it's there because clusters contain far more mass than we can see. The galaxies move too fast, and the hot gas is too hot for the visible matter alone to hold everything together. Without dark matter providing additional gravitational binding, clusters would simply fly apart. This was actually one of the earliest pieces of evidence for dark matter's existence. In the 1930s, Fritz Zwicky studied the Coma cluster and calculated that it needed about 400 times more mass than was visible to account for the motions of its galaxies. He called this missing mass Dunkel Materie, dark matter. Gravitational lensing provides dramatic visual proof of dark matter in clusters. When light from distant galaxies passes through a massive cluster, the cluster's gravity bends the light, creating distorted, stretched images called arcs. By mapping these distortions, astronomers can reconstruct the cluster's mass distribution. The results consistently show that mass is concentrated in regions where no visible matter exists, precisely where dark matter should be. Some clusters act as such powerful lenses that they magnify background galaxies, allowing astronomers to study objects that would otherwise be too faint to detect. The Hubble Space Telescope has captured stunning images of these lensing effects, with giant arcs and multiple images of the same distant galaxy appearing around massive foreground clusters. Galaxy clusters form at the intersections of cosmic filaments, the large-scale threads of matter that make up the universe's structure. If you could see the universe from outside and map all the galaxies, you'd see a web-like pattern, filaments connecting clusters, with vast voids between them. Clusters are like cities at highway intersections, where multiple routes meet and matter accumulates. They grow by accreting smaller groups and isolated galaxies that fall in along filaments. Once captured by a cluster's gravity, galaxies rarely escape. They become permanent residents, orbiting through the cluster for billions of years until they eventually merge with other galaxies or are tidally disrupted. The environment inside a cluster is hostile to star formation. As galaxies fall into a cluster, they plow through the hot intra-cluster medium. This creates ram pressure, essentially a headwind that strips gas out of the galaxy, removing the raw material needed to form new stars. Galaxies in clusters are systematically redder and more gas-poor than galaxies in less dense environments. They're dominated by old stars and have lower star formation rates. This process, called ram pressure stripping, can remove most of a galaxy's gas in just a few 100 million years. The stripped gas joins the intracluster medium, while the galaxy slowly reddens as its remaining stars age without replacement. The most massive clusters contain up to several thousand large galaxies and have total masses exceeding 10 to the power of 15 solar masses, 1,000,000 billion times the mass of the Sun. These extreme objects are rare, but they're crucial for cosmology. The abundance of galaxy clusters at different distances tells us about the universe's expansion history and the properties of dark energy. Clusters form where the universe's matter density is highest, and their growth over time is sensitive to how fast the universe is expanding. By counting clusters at different epochs and measuring their masses, astronomers can test cosmological models and constrain the properties of dark energy with remarkable precision. Some clusters have collided with each other, creating spectacular displays visible in X-ray observations. The Bullet Cluster, about 3.8 billion light-years away, is the aftermath of two galaxy clusters that smashed together at millions of kilometers per hour. The collision separated the cluster's components in a revealing way. The hot gas from both clusters collided and piled up in the middle, visible as bright X-ray emission. But the galaxies and dark matter passed through each other with little interaction, since both are mostly empty space gravitationally. Gravitational lensing shows that the mass is concentrated where the galaxies are, not where the hot gas is. This spatial separation between visible matter and gravitational mass provides compelling evidence that dark matter exists and behaves differently from normal matter. Superclusters are even larger structures that contain multiple galaxy clusters. The Laniakea supercluster, which includes our local group, spans 520 million light-years and contains roughly 100,000 large galaxies, with a total mass of 100 million billion solar masses. But superclusters aren't gravitationally bound. They're defined by the motion of galaxies within them. Galaxies in Laniakea are all being pulled toward a region called the Great Attractor, a gravitational anomaly hidden behind the Milky Way's disk. Superclusters are part of the cosmic web, connected to other superclusters by filaments and separated by voids. They represent the largest coherent structures in the universe, but unlike clusters, they will eventually be pulled apart by cosmic expansion. The cosmic web itself extends across the entire observable universe. Galaxy surveys have mapped this structure out to billions of light-years, revealing a remarkably consistent pattern. No matter which direction we look or how far we peer, the same web-like structure appears. Filaments, walls, clusters, and voids repeat on similar scales everywhere. This homogeneity on large scales is a key prediction of the standard cosmological model and strong evidence that our observations of the observable universe are representative of the universe as a whole. The cosmic web is thought to arise from tiny density fluctuations in the early universe, amplified over billions of years by gravity into the structures we see today. Redshift as a cosmic time indicator. When astronomers observe distant galaxies, they notice something peculiar. The light is shifted toward the red end of the spectrum. This phenomenon, called redshift, is the key to measuring cosmic distances and understanding the universe's expansion. It occurs because the space between us and distant galaxies is expanding, stretching the wavelength of light as it travels. The farther away a galaxy is, the more its light is redshifted. This relationship, discovered by Edwin Hubble in 1929, revolutionized our understanding of the cosmos and provided the first evidence that the universe is expanding. Redshift is quantified by the symbol Z. A galaxy with Z equals 1 has had its light wavelengths stretched by a factor of 2, doubled since the light was emitted. This means the universe has expanded by a factor of 2 since that light began its journey. A galaxy with Z equals 2 corresponds to a tripling of the universe's size, and so on. The most distant galaxies observed have redshifts exceeding Z equals 13, meaning we're seeing them as they were when the universe was less than 3% of its current size. These galaxies are among the first to form after the Big Bang. Their light stretched and dimmed by over 13 billion years of cosmic expansion. Converting redshift to physical distance isn't straightforward because the universe's expansion rate has changed over time. When the universe was younger, it expanded more slowly due to the decelerating effect of gravity. But about 5 billion years ago, dark energy began to dominate, causing expansion to accelerate. This means a galaxy at Z equals 1 is farther away than simple calculations would suggest if you assumed a constant expansion rate. Cosmologists use detailed models that account for dark matter, dark energy, and the universe's geometry to convert redshift into what's called co-moving distance, the distance to an object accounting for the expansion of space. The cosmic microwave background has a redshift of about Z equals 1100. This radiation was emitted when the universe was only 380,000 years old, and has been stretched by a factor of 1100 since then. Originally emitted as visible and infrared light from a hot plasma, it now reaches us as microwave radiation with a temperature of just 2.7 Kelvin. This extreme redshift tells us how much the universe has expanded since recombination, the moment when the universe cooled enough for atoms to form and light to travel freely. Everything we observe beyond the CMB is hidden from view, not because it doesn't exist, but because the universe was opaque to light at earlier times. High redshift galaxies look dramatically different from nearby galaxies. They're smaller, more irregular, and undergoing intense bursts of star formation. This makes sense because we're seeing them at an earlier stage of cosmic history, when galaxies were still assembling from smaller fragments. Many high redshift galaxies are merging, their shapes distorted by gravitational interactions. Star formation rates in these early galaxies can be 10 to 100 times higher than in typical galaxies today. They're forming stars at a frantic pace, converting their gas into stars much faster than galaxies in the local universe. This helps explain why present-day galaxies have so many stars. They formed most of them billions of years ago during this intense early phase. Quasars at high redshift are particularly interesting. These extremely luminous objects, powered by supermassive black holes consuming enormous amounts of matter, can be detected across most of the observable universe. The most distant quasars have redshifts around Z equals 7, corresponding to when the universe was only 770 million years old. The existence of billion solar mass black holes at such early times is puzzling. How did these black holes grow so massive so quickly? The standard model of black hole growth suggests they should still be relatively small at these early epochs. Their presence indicates that either black holes grew faster than expected, or that they formed with larger initial masses than current theories predict. Redshift surveys have mapped the three-dimensional distribution of galaxies across cosmic history. By measuring redshifts for millions of galaxies, astronomers can reconstruct how the cosmic web has evolved over billions of years. These surveys reveal that the large-scale structure has grown over time, with small density fluctuations in the early universe growing into the massive clusters, filaments, and voids we see today. The patterns in galaxy distribution at different redshifts match predictions from computer simulations of cosmic structure formation, providing strong support for the standard cosmological model. One complication is that redshift includes contributions from both cosmic expansion and the motion of galaxies through space. A galaxy moving toward us at high speed will have its light blue shifted, partially cancelling the cosmological redshift. A galaxy moving away adds to it. In clusters, where galaxies move at hundreds or thousands of kilometers per second, this peculiar velocity can create noticeable shifts. Astronomers must carefully account for these effects when using redshift to measure distances. For nearby galaxies, peculiar velocities can dominate over expansion, making redshift a poor distance indicator. But for galaxies beyond a few hundred million light-years, expansion dominates, and redshift becomes a reliable distance measure. The relationship between redshift and distance also depends on the universe's overall properties. If dark energy behaves differently than currently assumed, or if the universe's geometry isn't flat, the redshift-distance relationship changes. This is why measuring distances to distant objects is so important. It lets astronomers test cosmological models and constrain the properties of dark energy. Type Ia supernovae, with their consistent peak brightness, serve as excellent distance indicators that can be compared to redshift measurements. The discovery that high redshift supernovae are farther away than expected for their redshift led to the conclusion that cosmic expansion is accelerating, a finding that earned the 2011 Nobel Prize in Physics. Gravitational redshift is another effect, distinct from cosmological redshift, but equally important. Light escaping from a strong gravitational field loses energy, shifting toward longer wavelengths. This happens near massive objects like black holes and neutron stars. For light from the surface of a neutron star, gravitational redshift can be substantial, shifting spectral lines noticeably toward the red. Near the event horizon of a black hole, gravitational redshift becomes infinite. Light loses all its energy trying to escape and can never reach a distant observer. This is one reason why black holes appear black. Any light emitted from within or near the event horizon is redshifted into invisibility. Redshift will eventually limit what we can see. As the universe continues to expand and acceleration continues, distant galaxies will be pushed beyond the cosmic event horizon. Their light will be redshifted so severely that it becomes undetectable. In the far future, trillions of years from now, observers in the Milky Way, or whatever merged galaxy exists then, will see a much emptier universe. Most galaxies will have disappeared beyond the horizon, their light stretched to infinite wavelengths. Only the nearest gravitationally bound galaxies will remain visible. Future astronomers might conclude they live in a static, isolated galaxy in an otherwise empty universe. The same mistaken view astronomers held in the early 20th century before Hubble's discoveries. The universe expands faster than light at large scales. One of the most counterintuitive facts about the universe is that distant regions of space are moving away from us faster than the speed of light. This seems to violate Einstein's special relativity, which states that nothing can travel through space faster than light. But there's no violation here because space itself is expanding. Galaxies aren't moving through space at superluminal speeds. Rather, the space between us and them is growing so rapidly that the distance increases faster than light could cross it. This distinction is crucial. Special relativity limits motion through space, but it places no restrictions on how fast space itself can expand. The Hubble constant describes the current rate of expansion, about 70 kilometers per second per megaparsec. This means that for every megaparsec, 3.26 million light-years of distance, space is expanding at an additional 70 kilometers per second. For nearby galaxies, this produces relatively slow recession velocities. Andromeda, 2.5 million light-years away, should be receding at about 54 kilometers per second due to expansion, though its actual motion toward us at 110 kilometers per second is due to the gravitational attraction between our galaxies. But at larger distances, expansion dominates. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second, nearly a quarter of light speed. A galaxy 4,300 megaparsecs away recedes at exactly light speed. Beyond that distance, recession velocities exceed light speed. The cosmic event horizon sits at roughly 16 billion light-years in comoving distance. Galaxies beyond this horizon are receding faster than light, and light emitted from them today will never reach us. The expansion of space carries these photons away faster than they can approach, like a person running up a down escalator that's moving faster than they can run. However, we can still see these galaxies because we're looking at light they emitted billions of years ago when they were closer and receding more slowly. The observable universe extends to 46.5 billion light-years, well beyond the cosmic event horizon, because we're seeing ancient light from objects that are now beyond the horizon. This creates a strange situation. We can see galaxies that are currently unreachable. If we sent a light signal to them today, it would never arrive. The space between us is expanding too quickly. Yet we observe these galaxies as they were in the distant past when they were closer and reachable. Over time, as expansion continues, more and more of the galaxies we currently observe will cross the event horizon and become permanently unreachable. We'll continue to see them for billions of years, but we'll be looking at increasingly ancient light from when they were still on our side of the horizon. The mathematics of expansion reveals something remarkable. The more distant a region of space, the faster it recedes. This relationship is linear, which means there's no upper limit. If a galaxy at 4,300 megaparsecs recedes at light speed, then a galaxy at 8,600 megaparsecs recedes at twice light speed, and one at 43,000 megaparsecs at 10 times light speed. These aren't theoretical abstractions. Such galaxies exist within the observable universe. We see them, but they're now receding at multiple times the speed of light. The light we detect left them over 13 billion years ago, when they were much closer and receding much more slowly. Dark energy drives the acceleration of expansion. About 68% of the universe's total energy density is in the form of dark energy, a mysterious component that exerts negative pressure, pushing space apart. Unlike matter and radiation, whose density decreases as the universe expands, dark energy's density remains constant. This means that as the universe grows, dark energy comes to dominate over matter and radiation, accelerating expansion. This acceleration began about 5 billion years ago, when the universe had expanded enough for dark energy to become the dominant component. Before that, matter dominated, and expansion was decelerating under gravity's influence. The accelerating expansion has profound implications. Not only are distant galaxies receding faster than light, but their recession is speeding up. Galaxies that are currently just inside the cosmic event horizon will eventually cross it and become unreachable. The observable universe is losing galaxies. In the far future, only the local group and perhaps a few other nearby galaxies will remain visible. Everything else will have been carried beyond the horizon by accelerating expansion. This isn't just a theoretical concern for the distant future, it's happening now. The universe we can observe is gradually shrinking in terms of accessible content, even as the space itself expands. Faster-than-light expansion also affects communication. If we somehow detected a signal from an alien civilization in a galaxy currently receding faster than light, we could never reply. Even if we sent a message at light speed immediately upon receiving theirs, our message would make no headway against the expanding space. It would be swept backward, never reaching its destination. The civilization that sent the signal might have sent it billions of years ago when they were reachable, but they're unreachable now. This creates a form of cosmic isolation. Civilizations separated by sufficient distance cannot communicate, no matter how advanced their technology, because physics itself prevents information from crossing the expanding gulf between them. Measuring the expansion rate is one of cosmology's central challenges. Different methods give slightly different values for the Hubble constant, a discrepancy called the Hubble tension. Measurements using the cosmic microwave background predict a Hubble constant of about 67 km/s/MPC, while measurements using local distance indicators like supernovae give values around 73 km/s/MPC. This difference is small but statistically significant and has persisted despite improvements in measurement precision. Either there's an unidentified source of error in one or both methods, or there's new physics affecting the expansion rate. Resolving this tension is a major priority for observational cosmology. The expansion also means the universe was smaller and denser in the past. Extrapolating backward, the observable universe was once compressed into a region smaller than a single atom. This is the essence of the Big Bang model, not an explosion in space, but an expansion of space itself from an initial state of extreme density and temperature. The farther back we look, the smaller and hotter the universe was. At very early times, the universe was a hot, dense plasma, where matter and radiation were in thermal equilibrium. As expansion cooled it, particles combined into atoms, atoms into stars, and stars into galaxies. Everything we see arose from that initial dense state, carried outward by 13.8 billion years of expansion. Expansion of the universe through inflation. The observable universe, vast as it is, may be just a tiny fraction of the whole. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. During this period, space expanded faster than at any other time in cosmic history, increasing in size by a factor of at least 10 to the power of 26 in less than a microsecond. This incredible growth spurt solved several problems in cosmology, but also created a startling implication. The total universe must be far, far larger than the part we can observe. Inflation was proposed in the 1980s to explain why the universe appears so uniform. The cosmic microwave background has almost exactly the same temperature in every direction, 2.725 Kelvin, with variations of only about 1 part in 100,000. This uniformity is puzzling because regions on opposite sides of the sky are now so far apart that light hasn't had time to travel between them since the Big Bang. Without inflation, there's no reason these disconnected regions should have the same temperature. They couldn't have communicated or equilibrated thermally. Inflation solves this by proposing that all the observable universe was once much smaller, small enough for different regions to interact and reach thermal equilibrium. Then inflation stretched this tiny, uniform region to enormous size, creating the uniformity we observe today. Inflation also explains why space appears flat. The geometry of the universe depends on its density. Too much matter and it curves into a closed sphere. Too little and it curves into an open saddle shape, just the right amount, and it's flat like Euclidean geometry. Measurements show the universe is flat to within measurement errors. This is surprising because a flat universe requires a very specific density. If the actual density differs from this critical value by even a tiny amount early on, the universe quickly becomes obviously curved. Inflation solves this by stretching space so much that any initial curvature is flattened out, like inflating a balloon until its surface appears flat to an observer on it. The details of how inflation worked remain uncertain. The leading idea is that it was driven by a hypothetical scalar field called the inflaton, which existed in a high-energy state during the universe's first moments. As the inflaton field decayed to a lower energy state, it released enormous amounts of energy, driving exponential expansion. When inflation ended, this energy converted into matter and radiation, creating the hot, dense state described by the traditional Big Bang model. Inflation didn't replace the Big Bang, it extended it backward, adding a brief period of hyperacceleration before the hot expansion phase. One consequence of inflation is that the total universe must be much larger than the observable part. The observable universe is just the region that was within our past light cone, areas from which light has had time to reach us. But inflation stretched space so much that regions which were once within causal contact are now separated by distances far exceeding what light could travel in the age of the universe. Some estimates suggest the entire universe is at least 10 to the power of 23 times larger than the observable portion, possibly infinite. If the universe is infinite, it was always infinite, even at the moment of the Big Bang. Inflation just made the distances between any 2 points vastly larger. Quantum fluctuations during inflation seeded the structure we see today. At the quantum level, empty space is never truly empty. It's filled with virtual particles and field fluctuations that pop in and out of existence. During inflation, these quantum fluctuations were stretched to macroscopic scales. Regions that were slightly denser or less dense by quantum chance were amplified into the density variations that eventually grew into galaxies and galaxy clusters. This process is called quantum fluctuations seeding structure formation. The pattern of fluctuations predicted by inflation matches the observed pattern in the cosmic microwave background with remarkable precision, providing strong evidence that inflation occurred. Different regions of the universe may have stopped inflating at different times, leading to the concept of eternal inflation. In this scenario, inflation ends in some regions, like ours, but continues in others. These eternally inflating regions spawn new regions where inflation ends, which spawn their own inflating regions, ad infinitum. This creates a multiverse of bubble universes, each one a separate domain where inflation has ended. These bubble universes would be causally disconnected from each other, separated by regions of space still undergoing inflation. Our observable universe would be just one bubble in an infinite froth of universes, each potentially with different physical constants and laws. Testing inflation is challenging because most of its effects occurred at energies far beyond what we can probe in particle accelerators. The best evidence comes from observations of the cosmic microwave background. The pattern of temperature fluctuations in the CMB matches inflation's predictions. The spectrum of fluctuations, how their amplitude varies with angular scale, follows a nearly scale-invariant power law, exactly what inflation predicts. Alternative theories that don't include inflation struggle to explain this pattern. Additionally, inflation predicts the universe should be spatially flat, and measurements confirm this to high precision. One predicted signature of inflation that hasn't been detected yet is primordial gravitational waves. Inflation should have produced a background of gravitational waves, ripples in spacetime created by the violent expansion. These waves would leave a specific imprint on the polarization of the cosmic microwave background, a pattern called B modes. Several experiments are searching for this signal, but as of 2025, no confirmed detection has been made. Finding these B modes would be smoking gun evidence for inflation and would tell us about the energy scale at which inflation occurred. If inflation is correct, the observable universe is just a tiny patch of a much larger whole. Imagine looking at a pixel on a computer screen and trying to infer the size of the entire screen. That pixel might give you information about the screen's properties, its resolution, color depth, brightness, but it tells you nothing about the screen's total size. The observable universe is like that pixel. We can study its properties in detail, but we have no direct way to measure the full extent of the universe beyond our horizon. Inflation guarantees that whatever lies beyond is more of the same. More space, more matter, more galaxies, stretching far beyond our ability to observe. The philosophical implications are staggering. If the universe is truly enormous or infinite, then everything possible not only can happen, but must happen somewhere. There could be countless planets exactly like Earth, countless versions of human history playing out with minor variations, countless copies of you reading these words. This isn't mysticism. It's a straightforward consequence of infinite space with finite matter configurations. In an infinite universe, every possible arrangement of particles occurs infinitely many times. The observable universe contains about 10 to the power of 80 atoms. In an infinite universe, there are infinite regions with that same arrangement of atoms, including regions identical to our observable universe down to every quantum detail. Superstructures in the universe. For decades, astronomers believed there was a maximum size to cosmic structures. The cosmological principle states that on large enough scales, the universe should be homogeneous, it should look the same everywhere. This implies there's a scale beyond which you shouldn't find discrete structures, only uniform distribution of matter. But as telescope technology improved and surveys mapped larger volumes of space, astronomers kept finding bigger and bigger structures that challenged this principle. The Sloan Great Wall, discovered in 2003, stretches 1.37 billion light-years across. The Huge Large Quasar Group spans 4 billion light-years. And in 2013, astronomers announced the Hercules Corona Borealis Great Wall, a structure so vast it defies easy comprehension. The Hercules Corona Borealis Great Wall is a concentration of gamma-ray bursts and galaxies stretching more than 10 billion light-years across. To put that in perspective, light takes 10 billion years to cross from one end to the other, nearly 3/4 of the universe's current age. This structure is so large that it challenges theoretical models. According to calculations based on the cosmological principle, structures larger than about 1.2 billion light-years shouldn't exist. They wouldn't have had enough time to form through gravitational collapse in the universe's 13.8 billion-year history. Yet the Hercules Corona Borealis Great Wall exists, and it's 8 times larger than the theoretical limit. These giant structures are typically filaments or walls of galaxies, the densest parts of the cosmic web. They're not solid objects, but rather concentrations of galaxy clusters connected by filaments of dark matter and gas. The galaxies within them are still separated by millions of light-years, but their distribution is clearly non-random. There are so many more galaxies in these regions than average that they stand out as coherent structures when you map the universe on large scales. The Sloan Great Wall, for example, contains tens of thousands of galaxies arranged in a vast sheet-like structure. From certain angles, it appears as a dense concentration. From others, it's nearly invisible, revealing its sheet-like geometry. The discovery of these structures came from three-dimensional mapping of galaxy positions using redshift surveys. By measuring the redshift of millions of galaxies, astronomers can determine their distances and create three-dimensional maps of cosmic structure. When you plot galaxy positions in 3 dimensions, the cosmic web becomes visible, filaments connecting clusters, vast voids between them, and occasional enormous concentrations like the Great Walls. These surveys have now mapped billions of light-years of space in exquisite detail, revealing structure on every scale from individual galaxies to these largest known entities. What's particularly striking is that structure seems to exist at every scale we can observe. There are galaxy groups a few million light-years across, galaxy clusters tens of millions of light-years across, superclusters hundreds of millions of light-years across, and now these great walls stretching billions of light-years. There doesn't seem to be a clear cutoff where structure ends and homogeneity begins. This is slightly troubling for cosmology because the standard model predicts that beyond a certain scale, roughly 300 million light-years, the universe should appear essentially uniform. These giant structures suggest that either we're seeing statistical flukes, or there's something about structure formation we don't fully understand. One possibility is that these structures aren't as significant as they appear. When you map any random distribution, you'll occasionally find apparent patterns just by chance. With billions of galaxies to work with, some will inevitably cluster into patterns that look meaningful. Computer simulations of random distributions produce occasional large-scale structures purely by statistical fluctuation. Some astronomers argue that the Great Walls might be examples of this. They look impressive, but they're not necessarily physically bound structures. They might simply be chance alignments of unrelated galaxy clusters that happen to appear connected from our vantage point. However, other studies suggest these structures are real and significant. The Laniakea supercluster, for example, is defined not just by galaxy positions but by galaxy velocities. All galaxies in Laniakea are moving toward a common center, indicating gravitational influence across the entire structure. Similarly, the Shapley supercluster, one of the most massive structures in the nearby universe, contains more than 8,000 galaxies and has a total mass of about 10 to the power of 16 solar masses. Its gravitational pull affects galaxy motions across hundreds of millions of light-years. These are not random alignments. They're gravitationally meaningful structures that influence their surroundings. The existence of such large structures places constraints on cosmological models. Structure formation happens when overdense regions collapse under their own gravity, pulling in surrounding matter. The rate at which this occurs depends on the properties of dark matter and dark energy. If structures grow too slowly, you don't get the massive clusters and walls we observe. If they grow too quickly, you get far more structure than observed. By measuring the distribution of structure at different scales and different epochs, cosmologists can test whether their models of dark matter and dark energy are correct. So far, the models work well for most scales, but the very largest structures remain somewhat problematic. Future surveys will map even larger volumes of space, potentially finding even bigger structures, or determining that the Great Walls represent a genuine upper limit. The Dark Energy Spectroscopic Instrument, currently measuring redshifts for tens of millions of galaxies, will create the most detailed three-dimensional map of the universe ever made. If structures larger than 10 billion light-years exist, these surveys should find them. If they don't, that would suggest we've finally reached the scale where the cosmological principle holds and the universe truly becomes homogeneous. Either outcome would be scientifically valuable, either confirming current models or revealing new physics. The sheer scale of these structures challenges human comprehension in the same way that the observable universe itself does. A structure 10 billion light-years across is so large that describing it as big is almost meaningless. It's a significant fraction of the entire observable universe. If you could somehow view this structure from outside, it would span nearly a quarter of the visible cosmos. Light emitted from one end when dinosaurs first appeared on Earth would only now be reaching the other end. These structures aren't just large, They're comparable in scale to the age and extent of the universe itself, making them among the most extreme objects physics allows. Dark matter outweighs everything we can see. Every star, planet, nebula, and galaxy you've ever seen represents only about 15% of the universe's total matter content. The remaining 85% is dark matter, an invisible substance that doesn't emit, absorb, or reflect light. We can't see it directly, but its gravitational effects are undeniable. Dark matter holds galaxies together, binds galaxy clusters, and provides the gravitational scaffolding upon which all visible structure is formed. Without it, galaxies would fly apart, clusters wouldn't exist, and the cosmic web would never have formed. Dark matter is the universe's hidden skeleton, the invisible framework that supports everything we see. The evidence for dark matter comes from multiple independent observations. Galaxy rotation curves provided the first compelling evidence. When astronomers measured how fast stars orbit in spiral galaxies, they found something unexpected. In the solar system, outer planets orbit more slowly than inner planets because most of the sun's mass is at the center. Galaxies should work the same way. Stars far from the galactic center should orbit slowly. But observations show they orbit just as fast as stars closer in. The only way this works is if galaxies are embedded in massive halos of invisible matter extending far beyond the visible disk. Galaxy clusters provide even stronger evidence. The mass of a cluster can be calculated in 3 independent ways: by measuring the motions of galaxies within it, by observing the temperature of the hot intracluster gas, and by measuring gravitational lensing effects on background galaxies. All 3 methods agree. Clusters contain far more mass than can be accounted for by visible matter. The hot gas in clusters, despite containing more mass than all the galaxies combined, still represents only about 15% of the total mass. The rest is dark matter, distributed in a massive halo throughout and around the cluster. Gravitational lensing offers direct visual evidence. When light from a distant galaxy passes through a massive foreground object, the foreground's gravity bends the light, distorting the background galaxy's image. By mapping these distortions across many background galaxies, astronomers can reconstruct the foreground's mass distribution. The results consistently show mass concentrated in places where no visible matter exists. The Bullet cluster provides the most dramatic example. In this system, 2 galaxy clusters collided and passed through each other. The hot gas interacted and stayed in the center, but the dark matter halos passed through with minimal interaction. Gravitational lensing shows most of the mass is where the galaxies are, not where the gas is, exactly as dark matter theory predicts. The cosmic microwave background also requires dark matter. The pattern of temperature fluctuations in the CMB depends on the ratio of normal matter to dark matter in the early universe. Normal matter interacts with light, affecting how sound waves propagate through the early plasma. Dark matter doesn't interact with light, but its gravity affects how matter clumps. By analyzing the detailed pattern of CMB fluctuations, cosmologists can determine the relative amounts of normal and dark matter. The results match other measurements. Roughly 85% of all matter is dark matter. But what is dark matter? Despite decades of searching, we don't know. It's not made of ordinary atoms. Those emit light in various forms and would have shown up in observations. It's not antimatter, which would annihilate with regular matter and produce detectable gamma rays. It's not black holes or other dark compact objects. Surveys have ruled out significant amounts of such objects in the mass ranges needed to explain dark matter. Whatever it is, dark matter interacts with regular matter primarily through gravity. It doesn't seem to interact electromagnetically at all, and if it interacts through the weak nuclear force, those interactions are rare enough that we haven't detected them yet. The leading candidate is a new type of subatomic particle that hasn't been discovered yet. These hypothetical particles, called WIMPs for weakly interacting massive particles, would have been created in the Big Bang and would still be abundant throughout the universe. They'd have mass, so they'd interact gravitationally, but they wouldn't interact with light or other electromagnetic radiation. Dozens of experiments are searching for WIMPs by looking for the rare occasions when a dark matter particle might collide with an atomic nucleus in a detector. So far, no confirmed detection has been made, but the search continues with increasingly sensitive instruments. Alternative ideas include axions, extremely light particles predicted by some theories of particle physics, and sterile neutrinos, hypothetical cousins of regular neutrinos that interact even more weakly with regular matter. Some physicists have proposed modifying our theory of gravity instead of invoking new particles, suggesting that gravity behaves differently on galactic scales than Einstein's general relativity predicts. These modified Newtonian dynamics theories can explain some observations, but they struggle with others, particularly the detailed patterns in the cosmic microwave background and gravitational lensing in galaxy clusters. The distribution of dark matter shapes the universe. Computer simulations that include dark matter can successfully reproduce the cosmic web's structure, the filaments, clusters, and voids we observe. Simulations without dark matter fail to produce realistic structure. Dark matter's gravity pulls regular matter into clumps, where it can cool and form stars and galaxies. The first stars formed in the gravitational wells created by dark matter overdensities. Every galaxy sits at the center of a dark matter halo, with visible matter collected in the halo's deepest part. The Milky Way's dark matter halo probably extends 600,000 light-years or more from the galactic center, far beyond the visible disk. Dark matter even affects our solar system, though minimally. Earth is constantly passing through dark matter particles from the galaxy's halo, billions of them every second. They pass through us without interacting, ghosting through atoms as if they weren't there. The Sun and planets contain dark matter passing through them at all times. But because dark matter interacts so weakly, it has essentially no effect on planetary orbits or everyday physics. It's only on galactic scales, where vast amounts of dark matter accumulate, that its gravitational effects become significant. Despite not knowing what dark matter is, astronomers can map its distribution across the universe. Gravitational lensing surveys have created three-dimensional maps showing how dark matter is distributed in space. These maps reveal that dark matter follows the same large-scale structure as visible matter. It's concentrated in filaments connecting galaxy clusters, with voids between them. But dark matter's distribution is smoother than visible matter's. While galaxies and stars form sharp, concentrated structures, dark matter forms more diffuse halos. This makes sense because dark matter can't radiate energy and cool down the way normal matter does. It stays spread out in massive halos while normal matter collapses into compact objects. Massive black holes exceeding stellar systems. When most people think of black holes, they imagine stellar mass black holes formed when massive stars collapse. These range from about 3 to 100 solar masses and have event horizons a few hundred kilometers across. They're tiny on cosmic scales, but at the centers of most large galaxies lurk supermassive black holes, millions or billions of times more massive than the Sun, with event horizons that can span billions of kilometers, larger than the orbits of the outer planets. These behemoths dominate their galactic cores, influencing star formation, gas dynamics, and galactic evolution across thousands of light years. The supermassive black hole at the Milky Way center, Sagittarius A*, weighs 4.15 million solar masses. Its event horizon has a radius of about 12 million kilometers, 17 times the Sun's radius, but still small enough to fit comfortably inside Mercury's orbit. This might seem large by everyday standards, but it's actually one of the smaller supermassive black holes. The black hole at the center of M87, a giant elliptical galaxy 54 million light-years away, weighs 6.5 billion solar masses. Its event horizon is roughly 38 billion kilometers across, about 240 times the Sun-Earth distance. At this size, the event horizon would extend past Neptune's orbit in our solar system. Even M87's black hole isn't the largest. The black hole at the center of the galaxy, TUN 618, is estimated at 66 billion solar masses. Its event horizon spans roughly 1,300 astronomical units, about 11 light days across. It would take light 11 days to cross from one side to the other. To put this in perspective, the entire solar system out to the orbit of Neptune is only about 60 astronomical units across. Ton 618's black hole is more than 20 times larger than our entire planetary system. This object is so massive that its sphere of gravitational influence extends thousands of light years, affecting the motions of stars and gas clouds across a significant fraction of its host galaxy. How do black holes grow so large? Stellar mass black holes form from collapsing stars, but supermassive black holes can't form this way. Even the most massive stars produce black holes of only 100 solar masses or so. Building a billion solar mass black hole from stellar collapse alone would require merging 10 million stellar mass black holes, a process that would take far longer than the age of the universe. Instead, supermassive black holes likely form through different mechanisms. Either they begin as much larger seed black holes formed in the early universe, or they grow through sustained accretion of gas and mergers with other black holes over billions of years. Accretion is remarkably efficient at adding mass. When matter falls toward a black hole, it forms an accretion disk, a swirling disk of hot gas that gradually spirals inward. Friction within the disk heats it to millions of degrees, causing it to emit intense radiation. This radiation pushes away surrounding gas, limiting how fast the black hole can grow. There's a maximum accretion rate, called the Eddington limit, beyond which radiation pressure prevents more matter from falling in. For a billion solar mass black hole, the Eddington limit corresponds to adding about 20 solar masses per year. Even at this maximum rate, growing from a stellar mass seed to a billion solar masses would take hundreds of millions of years. Yet supermassive black holes existed when the universe was less than a billion years old. Quasars at redshifts of 6 or 7 are powered by black holes of a billion solar masses or more. And these quasars existed when the universe was only 800 million years old. There simply wasn't enough time for these black holes to grow from stellar seeds at normal accretion rates. Either they formed from much larger seeds, perhaps black holes of 100,000 solar masses created by the direct collapse of primordial gas clouds, or they grew faster than the Eddington limit would normally allow, possibly through super-Eddington accretion in the dense environments of the early universe. The relationship between black holes and their host galaxies is remarkably tight. The mass of a galaxy's central black hole is closely correlated with the mass of its bulge, the spherical concentration of stars at the galaxy's center. Galaxies with massive bulges have massive black holes, while galaxies with small bulges have smaller black holes. This suggests that black holes and galaxies grow together, influencing each other's evolution. When gas falls toward a black hole and forms an accretion disk, powerful jets and winds driven by the black hole's energy can blow gas out of the galaxy entirely, shutting down star formation. This process, called AGN feedback, may explain why the most massive galaxies stopped forming stars billions of years ago, despite containing vast amounts of gas. Supermassive black holes can merge when galaxies collide. When two galaxies merge, their central black holes sink toward the center of the merged galaxy due to dynamical friction, interactions with surrounding stars that slow the black holes down. Eventually, the black holes spiral toward each other and merge, releasing enormous amounts of energy in gravitational waves. The merger of two supermassive black holes is one of the most energetic events possible, briefly outshining all the stars in the universe combined in gravitational wave emission. The gravitational waves from such mergers ripple across the cosmos, and future space-based detectors like LISA will detect these signals, allowing astronomers to study supermassive black hole mergers across cosmic history. Near the event horizon, physics becomes extreme. The tidal forces, the difference in gravitational pull between your head and feet, become enormous. For a stellar mass black hole, you'd be torn apart long before reaching the event horizon, a process gruesomely called spaghettification. But for supermassive black holes, the tidal forces at the event horizon are much weaker because the horizon is so large. You could, in principle, fall through the event horizon of a billion solar mass black hole without being torn apart. You wouldn't even notice the moment you crossed it. Only later, as you fell deeper and space-time curvature increased, would tidal forces become fatal. Inside the event horizon, all paths lead to the singularity at the center. No matter which direction you try to move, you can't escape. The singularity isn't a place in space. It's a place in time, a moment in your inevitable future. Our understanding of physics breaks down at the singularity. General relativity predicts infinite curvature and infinite density, but these infinities signal that the theory is incomplete. A theory of quantum gravity, which we don't yet have, would be needed to describe what actually happens. The singularity might not exist as a point of infinite density. It might be replaced by something else, perhaps a region where space and time lose their conventional meanings. The shadows of supermassive black holes can be directly imaged. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the dark region created by the event horizon blocking light from the accretion disk behind it. The image showed M87's black hole, its shadow clearly visible against the glowing accretion disk. The shadow's size matched predictions from general relativity with remarkable precision, providing strong evidence that these objects truly are black holes, as Einstein's theory describes. In 2022, the EHT released an image of Sagittarius A's shadow, showing our own galaxy's central black hole for the first time. These images are technical marvels, requiring coordination of radio telescopes across the entire Earth to achieve the necessary resolution. The hidden multitude of galaxies. For decades, astronomers estimated the observable universe contained about 200 billion galaxies. This number appeared in countless textbooks and popular articles. It was based on deep surveys like the Hubble Deep Field, which stared at tiny patches of sky for days, revealing thousands of faint, distant galaxies. By counting galaxies in these deep fields and extrapolating to the entire sky, astronomers arrived at 200 billion. But in 2016, a study using improved analysis techniques suggested the true number might be 10 times higher, 2 trillion galaxies. This revision wasn't due to new observations. It came from better understanding of how many faint, distant galaxies earlier surveys had missed. The Hubble Deep Field images, taken in 1995, revolutionized our understanding of the distant universe. By pointing the Hubble Space Telescope at a tiny, apparently empty patch of sky and exposing for 10 days, astronomers captured light from nearly 3,000 galaxies, some so distant their light had traveled for over 12 billion years. This single image revealed that the universe is far more crowded with galaxies than anyone had suspected. Every direction we look, even in seemingly blank regions, contains countless galaxies. There are no empty directions in the sky, just directions where galaxies are too faint for our current telescopes to detect. Later, surveys pushed even deeper. The Hubble Ultra Deep Field, exposed for nearly a million seconds between 2003 and 2004, revealed about 10,000 galaxies in a region of sky roughly 1/10 the apparent size of the full moon. The Hubble Extreme Deep Field pushed deeper still, combining over 2,000 exposures taken over 10 years to detect some of the faintest and most distant galaxies ever observed. These galaxies appear as they were more than 13 billion years ago, less than 700 million years after the Big Bang. They're small, irregular, and undergoing intense star formation, snapshots of galaxy formation in action. But these surveys have limitations. They can only detect galaxies bright enough to register after days of exposure time. Fainter galaxies, either because they're intrinsically dim or because they're too distant, simply don't show up. The 2016 study used mathematical models to estimate how many galaxies should exist below Hubble's detection threshold. By analyzing the distribution of galaxies at different brightness levels and extrapolating to fainter magnitudes, researchers concluded that previous surveys had missed about 90% of galaxies in the observable universe. Most galaxies are small, faint dwarf galaxies that individually contribute little light, but vastly outnumber large galaxies like the Milky Way. This makes sense in the context of galaxy formation. Large galaxies like ours formed through mergers of smaller galaxies over billions of years. The early universe was full of small proto-galaxies, and many merged to form the mature galaxies we see today. But not all small galaxies merged. Many survive to the present day as dwarf galaxies. Our own local group contains dozens of them, tiny collections of a few million to a few billion stars. If this pattern holds across the universe, then small galaxies should vastly outnumber large ones. The updated count of 2 trillion galaxies reflects this expectation, accounting for the multitude of faint dwarfs that don't show up in most surveys. However, the 2 trillion figure comes with significant uncertainties. Extrapolating from observed galaxies to unobserved ones requires assumptions about how galaxy properties evolve with distance and redshift. Different assumptions lead to different total counts. Some analyses suggest the number could be even higher, while others argue it might be somewhat lower. What's certain is that the observable universe contains at least hundreds of billions of galaxies, and possibly trillions. The exact number depends on how you define a galaxy. At what point does a small collection of stars stop being a galaxy and become something else? These definitional questions matter when you're trying to count objects that span such a wide range of sizes and masses. Each galaxy contains hundreds of billions of stars on average. Multiply the number of galaxies by the average number of stars per galaxy, and you get approximately 10 to the power of 24 stars in the observable universe, a number so large it defies comprehension. That's about 100,000 stars for every grain of sand on Earth. If you could somehow count 1 star per second, it would take you 10 to the power of 16 years to count them all, about 1,000,000 times the current age of the universe. These numbers reveal the universe's true scale. It's not just big, it's incomprehensibly vast, filled with more stars than human minds can grasp. The distribution of these galaxies isn't uniform. As we've discussed, galaxies cluster into groups, clusters, and superclusters, forming the cosmic web. In some regions of space, galaxies are abundant, packed into clusters by the thousands. In other regions, the cosmic voids, galaxies are rare. The largest voids contain hardly any galaxies at all, across volumes hundreds of millions of light-years across. This clumpy distribution reflects the underlying dark matter structure and the initial density fluctuations from the early universe that seeded all structure formation. Future telescopes will census galaxies even more completely. The James Webb Space Telescope, launched in 2021, operates in infrared wavelengths, where distant galaxies shine brightest. Its deep surveys are detecting galaxies that formed when the universe was only 200 to 300 million years old, pushing our view back to the earliest epochs of galaxy formation. These observations will help pin down the total number of galaxies more accurately and reveal how galaxies evolved over cosmic time. Upcoming facilities like the Extremely Large Telescope and the Nancy Grace Roman Space Telescope will further refine our census, potentially revealing even fainter populations of galaxies that current instruments cannot detect. The sheer number of galaxies has implications for the search for extraterrestrial life. If even a tiny fraction of stars have planets, and even a tiny fraction of planets harbor life, and even a tiny fraction of life-bearing planets develop intelligent civilizations, the numbers still become staggeringly large. With 10 to the power of 24 stars in the observable universe, even odds of 1 in a billion still leave millions of potential civilizations. Of course, this is pure speculation. We have no data on how common life or intelligence actually is, but the scale of the universe makes the possibility hard to dismiss. With so many stars and galaxies, it would be surprising if Earth were the only place where life emerged. Yet the distances involved mean we may never know. Even if millions of civilizations exist scattered throughout the observable universe, most would be so far away that we could never detect them or communicate with them. Light from a civilization on the opposite side of the observable universe has taken 13 billion years to reach us. We're seeing them as they were in the ancient past, assuming they even exist. By now, they could have flourished and gone extinct billions of years ago. The combination of vast numbers of galaxies and vast distances between them creates a universe that is simultaneously crowded with potential and profoundly isolating. The first galaxies formed in complete darkness. The universe wasn't always filled with light. For roughly 400,000 years after the Big Bang, space was filled with a hot, opaque plasma that scattered light in every direction. Photons couldn't travel freely. They bounced endlessly between electrons and protons, trapped in the primordial fog. Then, as the universe expanded and cooled to about 3000 Kelvin, electrons and protons combined to form neutral hydrogen atoms. Suddenly, light could travel unimpeded. This moment, called recombination, released the cosmic microwave background radiation we see today. But after recombination came darkness. The universe entered what cosmologists call the Dark Ages, a period lasting several hundred million years when no stars existed to illuminate the void. During the Dark Ages, the universe consisted almost entirely of neutral hydrogen and helium, the two elements created in the Big Bang. These gases filled space uniformly at first, but tiny density variations, quantum fluctuations stretched to cosmic scales by inflation, began to grow under gravity's influence. Regions that were slightly denser pulled in surrounding matter, becoming denser still. Dark matter, which dominated the universe's mass, collapsed first into dense clumps called dark matter halos. These halos provided the gravitational wells where normal matter could collect. Gas clouds fell into these wells, compressed by gravity, and eventually reached densities and temperatures high enough for nuclear fusion to begin. The first stars ignited, ending the Dark Ages and beginning the cosmic dawn. These first stars were nothing like the Sun. Called population 3 stars, they formed from pristine hydrogen and helium containing no heavier elements. Without metals, astronomers' term for any element heavier than helium, to cool the gas efficiently, the collapsing clouds had to be much more massive before they could fragment and form stars. Population 3 stars were likely between 100 and 300 solar masses, giants that burned incredibly hot and bright, with surface temperatures exceeding 100,000 Kelvin. They shone with fierce ultraviolet radiation that ionized the surrounding hydrogen, creating expanding bubbles of ionized gas. These stars lived fast and died young, exhausting their fuel in just a few million years before exploding as supernovae. The death of population 3 stars seeded the universe with the first heavy elements. During their lives, nuclear fusion in their cores built progressively heavier elements: carbon, oxygen, silicon, iron. When they exploded, these elements scattered into space, mixing with the primordial hydrogen and helium. The next generation of stars formed from slightly enriched gas, allowing smaller stars to form. Over billions of years, successive generations of stars continued this process of chemical enrichment, gradually building up the concentrations of heavy elements needed for planets, life, and everything we see in the modern universe. The first galaxies were tiny compared to today's giants. They contained perhaps a few million stars, far smaller than the Milky Way's hundreds of billions. These protogalaxies formed when gas collected in the largest dark matter halos, typically a few hundred light-years across. Star formation was intense and chaotic, with massive stars forming, exploding, and enriching the gas in rapid cycles. Many of these early galaxies merged with neighbors, growing larger over time. The early universe was a violent place, with galaxies colliding and merging far more frequently than today. Through countless mergers over billions of years, these small proto-galaxies grew into the massive galaxies we observe in the modern universe. Observing the first galaxies is one of astronomy's greatest challenges. These objects are extremely distant, so their light has been traveling for over 13 billion years. Cosmological redshift has stretched their ultraviolet and visible light into infrared wavelengths. They're also incredibly faint, not only because of their distance, but because they're intrinsically small and contain fewer stars than modern galaxies. The Hubble Space Telescope detected some candidates for first-generation galaxies, but confirmation required spectroscopic follow-up to measure their redshifts precisely. The James Webb Space Telescope, optimized for infrared observations, is revolutionizing this field by detecting galaxies that formed when the universe was only 200 to 300 million years old. These observations reveal surprises. Some early galaxies are more massive and more structured than theoretical models predicted. Simulations suggested the first galaxies should be small and chaotic, but JWST has found galaxies at redshifts of 10 to 13 that already contain billions of stars and show signs of organized disk structure. Either stars formed more efficiently in the early universe than models assume, or some of these galaxies formed earlier than thought. These discoveries are forcing astronomers to revise their understanding of how quickly galaxies assembled in the universe's first billion years. Reionization, the process by which the universe transitioned from neutral to ionized, happened gradually over several 100 million years. The first stars and galaxies produced intense ultraviolet radiation that ionized the hydrogen in their immediate surroundings, creating bubbles of ionized gas. As more stars formed and more galaxies appeared, these bubbles grew and eventually overlapped, ionizing the entire universe. By about 1 billion years after the Big Bang, reionization was complete. The universe became transparent to ultraviolet light, as it remains today. Studying reionization tells astronomers about the abundance and properties of the first galaxies, which drove this cosmic phase transition. The scale of these early structures puts our place in cosmic history in perspective. When we look at the most distant galaxies observable, we're seeing light that left them over 13 billion years ago. At that time, these galaxies were only a few 100 million years old, cosmic infants compared to the 13.5 billion year old Milky Way. The stars we see in them have long since died. Those galaxies have since merged with others, grown enormously, and evolved into mature galaxies that might look very much like local galaxies today. We're not seeing these galaxies as they are, we're seeing their ancient past, fossils of cosmic youth preserved in the light that has traveled across most of the universe's history to reach us. The Dark Ages lasted longer than all of recorded human history. From recombination at 400,000 years after the Big Bang, to the first stars at perhaps 100 to 200 million years, the universe existed in darkness for a period 500 times longer than civilization has existed. During this time, space expanded, cooled, and prepared the conditions for structure formation. Dark matter halos grew, gas collected, and the stage was set for the cosmic drama that followed. This period left no direct observational record. The universe was dark, with no stars to observe, but its effects shaped everything that came after. The distribution of dark matter today, the large-scale structure of the cosmic web, even the properties of the cosmic microwave background, all carry imprints of processes that occurred during those dark centuries. The universe's hidden colossal voids. Between the filaments and clusters of the cosmic web lie the voids, enormous regions containing very few galaxies. These aren't completely empty, but they're remarkably underdense compared to the average universe. A typical void might contain only 10 to 20% of the average matter density, with galaxies scattered sparsely through volumes hundreds of millions of light-years across. The largest known void, the Boötes void discovered in 1981, spans roughly 330 million light-years. Inside this immense volume, astronomers have identified only about 60 galaxies, where a typical region of that size would contain thousands. Voids occupy the majority of the universe's volume, while galaxies, clusters, and filaments capture our attention, because that's where the interesting activity happens. The cosmic web structure is dominated by empty space. Roughly 80% of the universe's volume is in voids, with galaxies concentrated in the remaining 20% along filaments and in clusters. This means that a randomly selected point in space is far more likely to be in a void than near a galaxy. If you could teleport to a random location in the universe, you'd almost certainly find yourself in a dark, empty void, with only a few faint distant galaxies visible in any direction. Voids form from regions that were slightly underdense in the early universe, while overdense regions collapsed under gravity to form galaxies and clusters. Underdense regions expanded faster than average. As structure formed, galaxies that happened to be near the edges of underdense regions were pulled away by the gravitational attraction of nearby overdense regions. Over billions of years, this process evacuated voids of most of their matter, with galaxies migrating toward the filaments and clusters that bound them. The result is the foam-like structure we observe: dense regions connected by filaments, surrounding vast empty voids. The galaxies that do exist in voids tend to be different from galaxies in denser environments. Void galaxies are typically smaller, bluer, and forming stars more actively than galaxies in clusters. This makes sense because they've experienced fewer interactions and mergers. In dense environments, galaxies frequently collide, triggering bursts of star formation that quickly consume available gas. Ram pressure stripping removes gas from galaxies, moving through hot, intracluster medium. But void galaxies evolve in isolation, steadily forming stars from their gas reservoirs without external interference. They represent a different evolutionary pathway, showing what happens to galaxies when left alone. Despite their emptiness, voids aren't completely devoid of matter. Dark matter fills voids just as it fills all of space, though at lower density than average. There's also gas, primarily neutral hydrogen, spread thinly through void interiors. This gas can be detected through its absorption of light from background quasars, a technique that reveals vast clouds of hydrogen in seemingly empty regions. The gas density is extremely low, far lower than the intergalactic medium in galaxy clusters, but integrated over the enormous volumes involved, voids contain significant amounts of matter. It's just spread so thinly that it's nearly invisible. The expansion of voids tells us about dark energy. As the universe expands, voids grow larger. Since voids contain relatively little matter, there's little gravitational attraction to slow their expansion. Instead, dark energy's repulsive effect dominates, causing voids to expand faster than the universe's average expansion rate. By measuring how void sizes change over cosmic time, astronomers can constrain the properties of dark energy and test whether its strength has remained constant or changed. Current observations suggest dark energy has remained roughly constant, but future surveys measuring void evolution will test this with greater precision. Void statistics provide a unique probe of cosmic structure. While most studies focus on where galaxies are, void studies focus on where they aren't. The size distribution of voids, their number density at different epochs, and their internal structure all depend on cosmological parameters like the matter density, dark energy properties, and the amplitude of primordial density fluctuations. By mapping voids in large galaxy surveys, cosmologists can extract information complementary to what they learn from studying clusters and filaments. Voids are sensitive to different aspects of structure formation, making them valuable tools for testing cosmological models. Some voids appear to be expanding, pushing galaxies away from their centers. This isn't just the general expansion of the universe, it's an additional outflow caused by the void's underdensity. Galaxies near void edges feel a net gravitational pull toward the surrounding filaments and away from the void's low-density interior. This creates coherent flows of galaxies away from void centers, a phenomenon detected through careful measurements of galaxy peculiar velocities. These flows, extending over hundreds of millions of light-years, represent some of the largest coherent motions in the universe. The existence of voids raises questions about the universe's homogeneity. The cosmological principle states that on large enough scales, the universe should look the same everywhere, but voids are hundreds of millions of light-years across, comparable to the distance light travels in a significant fraction of the universe's age. At what scale does the universe become truly homogeneous? Current surveys suggest that by scales of about 300 to 500 million light-years, the matter distribution becomes relatively uniform. But individual voids can approach this size, and structures like the Hercules Corona Borealis Great Wall exceed it. Whether these represent genuine violations of homogeneity or statistical fluctuations remains debated. Living in a void would provide a very different view of the universe. An observer in the center of a large void would see very few nearby galaxies. The night sky would be profoundly dark, with only scattered faint smudges representing the nearest galaxies tens of millions of light-years away. The cosmic microwave background would still be visible, but the sense of being in a vast, galaxy-rich universe would be absent. Interestingly, some have speculated that we might live in a small void, which could affect our measurements of cosmic expansion. If we're in a slightly underdense region, the expansion rate we measure locally might differ from the universe's average expansion rate. However, current evidence suggests we're not in any significant void. Our local environment appears fairly typical. Mapping the infant universe. The cosmic microwave background is the oldest light in the universe, emitted when the cosmos was only 380,000 years old. Before this moment, the universe was filled with hot ionized plasma so dense that photons couldn't travel freely. They scattered constantly off free electrons, trapped in the primordial soup. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. Suddenly, photons could travel unimpeded. The universe became transparent, and the light emitted at that moment has been traveling through space ever since, cooled and stretched by expansion, into microwaves we detect today at a temperature of 2.725 Kelvin. When we observe the CMB, we're looking at a surface called the surface of last scattering, the spherical shell surrounding us from which the CMB photons were emitted. This surface is now about 46 billion light-years away due to the expansion of space since the light was emitted. It represents the edge of the observable universe, the farthest we can see with electromagnetic radiation. Beyond this surface, the universe was opaque. We cannot see farther back in time with light because earlier epochs were too hot and dense for photons to travel freely. The CMB is our ultimate horizon, the earliest snapshot of the universe that light can provide. The CMB's temperature is remarkably uniform across the sky, varying by only about 1 part in 100,000. This incredible uniformity is what makes the CMB so valuable. The tiny temperature variations that do exist, measured precisely by satellites like COBE, WMAP, and Planck, represent density fluctuations in the early universe. Slightly denser regions were slightly hotter, producing slight temperature variations in the CMB. These are the seeds from which all structure grew. Over billions of years, overdense regions collapsed under gravity, forming galaxies, clusters, and the cosmic web. The pattern of fluctuations in the CMB encodes information about the universe's composition, geometry, age, and the physics that governed its early moments. Analyzing the CMB reveals the universe's fundamental properties with astounding precision. The Planck satellite's measurements determined the universe's age to be 13.787 billion years, plus or minus 20 million years. They measured the Hubble constant, the matter and dark energy densities, and confirmed that space is flat to within a fraction of a percent. The CMB's power spectrum, a graph showing how the amplitude of temperature fluctuations varies with angular scale, matches theoretical predictions from the standard cosmological model almost perfectly. This agreement is one of the strongest confirmations that our understanding of cosmic history is fundamentally correct. The CMB also reveals the baryon acoustic oscillations, sound waves that propagated through the early universe's plasma. Before recombination, photons and baryons were coupled together in a hot plasma. Pressure waves rippled through this plasma, creating regions of compression and rarefaction. When recombination occurred, these waves froze in place, imprinted as subtle variations in the CMB's temperature and in the distribution of matter. The characteristic scale of these oscillations, about 500 million light-years in today's universe, appears as a preferred scale in galaxy distributions. By measuring this scale, astronomers can determine the universe's expansion history and constrain dark energy's properties. Polarization of the CMB provides additional information. When CMB photons scattered off electrons during recombination, they acquired slight polarization. Their electromagnetic waves aligned in particular directions. This polarization has two components, E modes and B modes. E modes have been detected and match predictions from density fluctuations. B modes would be produced by primordial gravitational waves from inflation, but despite extensive searches, no confirmed detection exists yet. Finding B modes would be smoking gun evidence for inflation and would tell us about the energy scale at which inflation occurred, providing a window into physics at energies far beyond what particle accelerators can reach. The CMB's dipole anisotropy reveals our motion through space. Because we're moving relative to the CMB's rest frame at about 370 kilometers per second, the CMB appears slightly hotter in the direction we're moving and cooler in the opposite direction. This Doppler shift creates a dipole pattern with an amplitude about 100 times larger than the intrinsic temperature fluctuations. Subtracting this dipole reveals the much smaller fluctuations from the early universe. Our motion isn't just Earth's orbit or the Sun's motion through the galaxy. It's the peculiar velocity of the entire local group, pulled by the gravitational attraction of massive structures like the Virgo and Hydra Centaurus superclusters. The CMB also constrains exotic physics. If the universe went through unusual phases in its early history, extra dimensions, phase transitions, cosmic strings, or other phenomena, these would leave detectable signatures in the CMB. The fact that the CMB matches simple models so well limits how exotic the early universe could have been. Any new physics must produce effects small enough that they don't significantly alter the CMB's observed properties. This has ruled out many speculative theories and constrains parameters in theories that remain viable. Foreground emissions complicate CMB observations. Microwaves from our galaxy, synchrotron radiation, thermal dust emission, and free emission contaminate the CMB signal. Extragalactic sources like radio galaxies and dusty star-forming galaxies also contribute foreground noise. Cosmologists must carefully model and subtract these foregrounds to isolate the true CMB signal. This requires observations at multiple frequencies to distinguish the CMB's characteristic blackbody spectrum from foreground emissions with different spectral properties. The Planck satellite observed at 9 different frequencies specifically to enable precise foreground subtraction. The CMB will remain the best window into the early universe for the foreseeable future. Future experiments aim to detect B-mode polarization with sufficient sensitivity to confirm or rule out inflationary models. Ground-based experiments in Antarctica and Chile, balloon-borne telescopes, and proposed space missions will continue mapping the CMB with increasing precision. Each improvement in sensitivity allows tests of more subtle predictions and tighter constraints on cosmological parameters. The CMB has already revolutionized cosmology once. Its continued study promises to reveal even more about the universe's birth and evolution. Time dilation across the cosmos. One of general relativity's strangest predictions is that time flows at different rates depending on gravitational fields and relative motion. Near massive objects, time runs slower than in empty space. For objects moving at high speeds, time dilates relative to stationary observers. These aren't just theoretical curiosities, they're measurable effects with profound implications for understanding the universe's scale and structure. Gravitational time dilation means that clocks on Earth run slower than clocks in orbit, an effect GPS satellites must account for to maintain accuracy. But these effects become dramatic on cosmic scales, particularly near extreme objects like black holes and neutron stars. Near the event horizon of a black hole, time dilation becomes severe. If you watched a clock falling toward a black hole, you'd see it tick slower and slower as it approached the horizon. At the horizon itself, time appears to stop completely from your perspective. The clock would freeze, never quite reaching the horizon, despite falling toward it forever. Of course, from the perspective of an observer falling with the clock, nothing unusual happens. They'd fall through the horizon in finite time by their own clock. The discrepancy arises because gravitational fields warp spacetime differently for different observers. There's no single universal time. Time is relative to the observer's motion and position in the gravitational field. Cosmological time dilation affects how we observe distant objects. When we look at a galaxy billions of light years away, we're seeing it as it was billions of years ago when the universe was younger and smaller. But we're also seeing it in slow motion. A supernova that takes 20 days to brighten and fade in its rest frame appears to take much longer when observed at high redshift. A supernova at redshift z equals 1 appears stretched in time by a factor of 2. A 20-day event appears to last 40 days. This effect has been directly observed in Type Ia supernova at various redshifts, confirming that time flows slower in the past reference frame compared to ours. This might sound paradoxical, but it's a natural consequence of how space-time works. As the universe expands, it carries galaxies apart and stretches the wavelength of light traveling between them. This stretching affects time as well as space. From our perspective, watching a distant galaxy, all processes in that galaxy appear slowed by the redshift factor. Their stars burn more slowly, their supernovae explode more slowly. Even the ticking of hypothetical clocks would appear slowed. This isn't an illusion, it's how time actually flows for observers separated by cosmological distances in an expanding universe. Gravitational time dilation near massive objects creates permanent differences in elapsed time. Imagine two stars form simultaneously, one in intergalactic space and one orbiting close to a supermassive black hole. The star near the black hole experiences strong gravitational time dilation. Time runs slower for it than for the star in intergalactic space. If both stars live for 10 billion years by their own measure, an external observer would see them end their lives at different times. The star in free space would die first, billions of years before the star near the black hole, even though both experience the same subjective lifespan. The universe's age isn't absolute. It depends on where you measure it from. This has implications for understanding the universe's structure. The cosmic microwave background tells us the universe is 13.787 billion years old, but that's measured in a specific reference frame. Essentially, the frame co-moving with the average expansion. Observers in different locations and gravitational potentials would measure slightly different ages. These differences are typically small for normal astronomical environments, but can become significant near extreme objects. An observer on a planet orbiting very close to a supermassive black hole might measure the universe's age as only a few billion years, despite the CMB telling distant observers it's nearly 14 billion years old. Velocity time dilation affects fast-moving objects, stars orbiting close to Sagittarius. The Milky Way's central black hole, reach velocities of several percent of light speed. At such speeds, time dilation becomes noticeable. A star orbiting at 5% of light speed experiences time running about 0.1% slower than a distant stationary observer. Over millions of years, this adds up. The fast-moving star ages slightly less than stars in the galactic disk. For objects moving at near light speed, the effect is dramatic. At 90% of light speed, time runs at about 44% of the rate experienced by a stationary observer. At 99.5% of light speed, it's about 10%. Particles in cosmic rays, traveling at 99.9999% of light speed, experience time running thousands of times slower than we do. These relativistic effects complicate the notion of the universe having a single age. Different observers following different paths through space-time will measure different elapsed time since the Big Bang. The 13.787 billion year figure is the time measured by an observer who has been moving with the Hubble flow, neither falling into overdense regions nor being ejected from them, just coasting along with the average expansion. Real observers, bound in galaxies and clusters, have followed more complicated paths and thus measure slightly different ages. These differences are small on average, but illustrate that cosmic time isn't absolute, it's frame-dependent. Gravitational waves also experience time dilation. When LIGO detects gravitational waves from merging black holes, the signal's frequency depends on the source's redshift. A merger producing a signal at 100 Hz in its rest frame would produce a 50 Hz signal at redshift z equals 1. This gravitational wave redshift provides another way to measure cosmic distances and test the expansion history. As gravitational wave astronomy matures and detects more distant sources, these measurements will complement electromagnetic observations in constraining cosmology and probing the universe's structure. The relativity of time has philosophical implications for understanding cosmic history. Events that appear simultaneous from one perspective may not be from another. The Big Bang itself, was it a single moment everywhere or different moments depending on reference frame? In cosmology, we define cosmic time as the time measured by co-moving observers, but this is a choice of convenience, not a fundamental truth. Space-time is a four-dimensional structure, and different slicing choices produce different notions of simultaneity. The universe's history is better thought of as a four-dimensional space-time structure than as a three-dimensional space evolving through absolute time. The observable universe as historical light. Every photon our telescopes detect is historical. Light from the Sun takes 8 minutes and 20 seconds to reach Earth, so we see the Sun as it was 8 minutes ago. If the Sun exploded right now, we wouldn't know for over 8 minutes. Light from Alpha Centauri takes 4.37 years, so we see that star system as it was 4.37 years in the past. The farther we look, the farther back we see. This isn't a limitation of technology. It's a fundamental consequence of the finite speed of light. We can never see the universe as it is right now. We can only observe its past, with the look-back time increasing linearly with distance for nearby objects, and more complicatedly for distant ones due to cosmic expansion. For the nearest galaxies, this delay is manageable. Andromeda is 2.5 million light-years away, so we see it as it was 2.5 million years ago. In the scheme of galactic evolution, 2.5 million years is insignificant. Not enough time for major changes. We're seeing Andromeda almost as it is now, give or take some stellar births and deaths. But for more distant galaxies, the light travel time becomes a significant fraction of cosmic history. A galaxy 5 billion light-years away appears as it was 5 billion years ago, before Earth even existed. We're not just seeing it from a great distance, we're seeing it at a completely different epoch of cosmic history. The most distant galaxies we observe appear as they were over 13 billion years ago, less than 700 million years after the Big Bang. These galaxies exist now, in the present moment defined by our reference frame, but we have no way to see what they currently look like. The light showing their present state has not yet reached us, and won't for billions of years. In the meantime, those galaxies have evolved dramatically. Many have merged with neighbors, grown to many times their early size, formed trillions of stars, and settled into mature spiral or elliptical shapes. But we see none of this. We see only their ancient past, frozen in the light that left them eons ago. This creates a strange asymmetry. We can observe the universe's past in great detail, but know almost nothing about its present state beyond our immediate cosmic neighborhood. Everything farther than a few million light-years is shown to us in progressively older states. The universe appears as a time gradient, with nearby regions shown relatively recently and distant regions shown in the ancient past. If we could somehow see the entire observable universe simultaneously in its present state, it would look dramatically different from what we observe. Most distant galaxies would appear larger, more evolved, and likely merged with others. Many galaxies we see separately would have already collided and combined. This has profound implications for testing cosmological models. When astronomers observe galaxies at different distances and compare their properties, they're comparing galaxies at different ages. A galaxy at redshift 2 is being seen as it was about 10 billion years ago, while a similar galaxy at redshift 0.5 is seen from about 5 billion years ago. Differences between them reflect not just spatial variation, but temporal evolution. Cosmologists must carefully account for this when studying how galaxy properties correlate with environment or testing theories of structure formation. The distance-redshift-age relationship complicates every observational study of cosmic structure. The light travel time also affects how we think about causality across cosmic distances. If a galaxy 10 billion light-years away exploded today, we wouldn't see it for 10 billion years. By the time the light reached us, the universe would be much older, possibly double its current age depending on how expansion continues. Any information about present events in that galaxy is causally disconnected from us. It exists in our future light cone, events that could in principle affect us but haven't yet. The vast majority of the present-day universe is causally disconnected from us. We can't see it, we can't affect it, and it can't affect us. This makes the universe seem even larger than distance measurements suggest. It's not just that galaxies are far away in space, they're far away in time. The observable universe is really a past light cone, a cone-shaped region of space-time containing all events from which light has had time to reach us. The universe's present state, defined by our reference frame's notion of simultaneity, extends far beyond what we can observe. Galaxies beyond the cosmic horizon exist right now in the present moment, but we'll never see them because their light will never reach us. The present-day universe is fundamentally unobservable except for our immediate vicinity. Future astronomers will face an even more limited view. As cosmic expansion accelerates, more galaxies will cross the cosmic event horizon, disappearing beyond our ability to ever receive light from them. In the far future, trillions of years from now, an observer in what remains of the Milky Way will see almost no other galaxies. The sky will be profoundly dark, with only the nearest gravitationally bound companions visible. They'll have no way to observe the cosmic microwave background. It will have redshifted into undetectability. They'll have no evidence of the Big Bang, no ability to measure cosmic expansion, no indication that the universe is anything other than a single, static galaxy in empty space. Their observational horizons will have shrunk so much that reconstructing cosmic history would be nearly impossible without inherited knowledge from earlier eras. We're fortunate to live in an epoch when the universe is observable. The galaxies we see, the cosmic microwave background, the large-scale structure, all of this is visible to us because we exist at a time when light from the early universe has reached us, but hasn't yet been carried away by accelerating expansion. In cosmic terms, we're living in a special window of observability. Billions of years ago, much of what we see today hadn't yet come into view. Billions of years from now, much of what we see will have disappeared beyond the horizon. The universe's observability is time-dependent, and we happen to exist when conditions are optimal for cosmology. This temporal limitation affects our ability to answer ultimate questions. We can't directly observe whether the universe is infinite or finite beyond the observable portion. We can't see what's happening right now in distant galaxies. We can't test whether the laws of physics are the same everywhere in the present-day universe, only whether they were the same at different times in the past. Our picture of the cosmos is necessarily historical, stitched together from ancient light, carrying information about bygone eras. The universe as it exists right now, in all its vastness and complexity, remains forever beyond our direct observation. We can only infer, extrapolate, and imagine what lies beyond the horizon of time and space. Neutron star density beyond comprehension. When massive stars explode as supernovae, their cores can collapse into neutron stars, objects so dense that a sugar cube-sized chunk would weigh as much as Mount Everest. A typical neutron star contains 1.4 solar masses, compressed into a sphere only about 20 kilometers across. This makes them the densest objects in the universe besides black holes. The matter in a neutron star's core exists in states that can't be replicated anywhere else, with densities exceeding that of atomic nuclei. At these extreme densities, protons and electrons merge to form neutrons, creating a star made almost entirely of neutrons packed so tightly that they touch each other. The surface gravity on a neutron star is about 2 billion times stronger than Earth's. If you could somehow stand on a neutron star's surface, you'd weigh 200 billion times more than you do on Earth. The escape velocity is about 100,000 kilometers per second, one-third the speed of light. This intense gravity creates extreme time dilation. A clock on a neutron star's surface runs about 30% slower than a clock far from any gravitational field. The star's gravity also warps space-time dramatically, bending light rays and allowing you to see around the star's curve. You could actually see part of the far side of the star by looking straight ahead, as light from the back curves around to reach you. Some neutron stars spin at incredible rates. Pulsars are neutron stars that emit beams of radio waves from their magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second. Its equator is moving at about 24% of light speed. At these rotation rates, the star is nearly at its stability limit. Spin it much faster and centrifugal forces would tear it apart. The fact that such rapid rotation is possible tells us something profound about the strength of neutron star matter. Normal atomic matter would disintegrate at far lower rotation rates. Only the exotic nuclear matter in neutron stars can withstand such extreme conditions. Neutron stars possess the strongest magnetic fields in the universe. A typical pulsar has a magnetic field strength of about 1 trillion Gauss, 1 billion times stronger than the strongest magnetic fields we can produce on Earth. Magnetars, a special class of neutron stars, have fields up to 1,000 times stronger still, reaching 10 to the power of 15 Gauss. These fields are so intense they affect the quantum vacuum itself, causing it to polarize and creating bizarre optical effects. The magnetic field's energy density exceeds the mass energy of normal matter. If you got too close to a magnetar, say within 1,000 kilometers, the magnetic field would be strong enough to fatally disrupt the molecular bonds in your body. The interior structure of neutron stars remains mysterious. The outer layer, called the crust, is made of atomic nuclei embedded in a sea of electrons, somewhat like ordinary matter, but at much higher density. Below this, densities increase until nuclei merge into a continuous nuclear matter soup. The exact state of matter in the core is uncertain. At such extreme densities, quarks, the particles that make up protons and neutrons, might become deconfined, creating quark matter. Some theories predict stranger possibilities: pion condensates, kaon condensates, or even strange quark matter. The physics at these densities is at the edge of what we understand, and neutron stars are the only natural laboratories where such conditions exist. When two neutron stars collide, they produce some of the most energetic events in the universe. The collision releases more energy in a second than the sun will produce in its entire lifetime. Gravitational waves ripple out across space-time, carrying information about the collision's violence. The impact ejects neutron-rich matter that undergoes rapid neutron capture, synthesizing heavy elements like gold, platinum, and uranium. Nearly all the gold in the universe, including the gold in your jewelry, was created in neutron star collisions. The 2017 detection of gravitational waves from colliding neutron stars, followed by observations of the electromagnetic afterglow, confirmed these cosmic factories of heavy elements and opened the era of multi-messenger astronomy. Neutron stars challenge our understanding of matter's behavior under extreme conditions. The equation of state, the relationship between pressure and density for nuclear matter, remains uncertain at neutron star densities. Different theoretical models predict different maximum masses for neutron stars. Observations of especially massive neutron stars like PSRJ 0740 plus 6620 at 2.14 solar masses constrain these models. If we ever detect a neutron star more massive than about 2.5 solar masses, it would revolutionize nuclear physics. Such an object would require exotic forms of matter or new physical interactions to remain stable against gravitational collapse into a black hole. The study of neutron stars connects astrophysics and nuclear physics in unique ways. By observing how neutron stars behave, their maximum masses, their radii, how they deform under rotation, physicists can learn about nuclear forces at densities impossible to achieve in laboratories. The NICE mission on the International Space Station measures neutron star radii with unprecedented precision by observing how X-rays from their hot surfaces vary as the stars rotate. These measurements test nuclear theory and help determine whether exotic matter exists in neutron star cores. Despite being called neutron stars, these objects aren't made entirely of neutrons. The crust contains protons and electrons, and the interior likely contains a mixture of neutrons, protons, electrons, and possibly other exotic particles. The exact composition affects observable properties like cooling rates and oscillation frequencies. When neutron stars experience starquakes, sudden shifts in their crust, they release energy that alters their rotation rate slightly. These glitches have been observed in many pulsars and provide clues about the star's internal structure. Some pulsars show anti-glitches, slowing down slightly, which might indicate the presence of a superfluid core rotating at a different rate than the crust. The scale of neutron stars is deceptive. They're only 20 kilometers across. You could drive around one in about an hour at highway speeds. Yet they contain more mass than the Sun, which is 1.4 million kilometers in diameter. If the Sun were compressed to neutron star density, it would fit inside a small city. If Earth were compressed to this density, it would be about 300 meters across, roughly the size of a large sports stadium. These comparisons illustrate how utterly alien neutron star matter is compared to anything in our experience. The gap between everyday matter and neutron star matter is as vast as the gap between different cosmic structures. Quasars powered the universe's most violent era. Quasars are the most luminous, persistent objects in the universe, outshining entire galaxies despite originating from regions smaller than our solar system. These brilliant beacons are powered by supermassive black holes at the centers of distant galaxies, actively consuming enormous amounts of matter. As gas spirals into the black hole, it forms an accretion disk heated to millions of degrees. The disk radiates across the electromagnetic spectrum, from radio waves to X-rays. Some quasars are so luminous they emit energy equivalent to trillions of suns. The brightest known quasar, J05294351, has a luminosity of about 500 trillion solar luminosities, enough to outshine thousands of Milky Way galaxies combined. The era of quasars peaked when the universe was between 2 and 3 billion years old. During this epoch, galaxy mergers were far more common than today, and gas was more abundant and less enriched with heavy elements. These conditions created ideal environments for black holes to grow rapidly. Gas funneled into galactic centers during mergers, providing fuel for accretion. The universe was brighter on average than it is now, not from stars but from accreting black holes. If you could transport yourself to this era, the sky would be filled with brilliant points of light, quasars scattered throughout space like cosmic lighthouses. Observing distant quasars reveals the universe as it was billions of years ago. The most distant quasars have redshifts exceeding 7, meaning we see them as they were less than 800 million years after the Big Bang. These early quasars host black holes of 1 billion solar masses or more, raising puzzles about how such massive black holes formed so quickly. The standard theory of black hole growth suggests they should still be much smaller at these early times. Either they started from unusually massive seeds, perhaps 100,000 solar mass black holes, formed by direct collapse of primordial gas clouds, or they grew through super-Eddington accretion, consuming matter faster than theoretical limits normally allow. Quasars serve as backlight sources for studying the intervening universe. As quasar light travels across billions of light years, it passes through clouds of gas in intergalactic space. These clouds absorb specific wavelengths, creating absorption lines in the quasar's spectrum. By analyzing these lines, astronomers can map the distribution of hydrogen, helium, and metals throughout cosmic history. The Lyman alpha forest, a series of absorption lines from neutral hydrogen, provides a three-dimensional map of intergalactic gas. This technique has revealed how the intergalactic medium evolves over time, becoming more ionized and metal-enriched as successive generations of stars enrich it. Some quasars produce enormous jets of plasma traveling at nearly light speed. These jets extend hundreds of thousands or even millions of light years from the quasar, dwarfing the host galaxy. The jets are created by magnetic fields threading the accretion disk, which accelerate particles to relativistic speeds and channel them along the black hole's rotation axis. When these jets point toward Earth, the quasar appears even brighter due to relativistic beaming. The radiation is concentrated in the direction of motion. These blazars can vary dramatically in brightness over days or weeks, as turbulence in the jet creates bright spots that sweep across our line of sight. The energy released by quasars affects their host galaxies profoundly. Powerful winds driven by radiation pressure can blow gas out of the galaxy entirely, shutting down star formation. This AGN feedback process is thought to explain why the most massive galaxies stopped forming stars billions of years ago, despite containing vast amounts of gas. The quasar phase is self-limiting. As it ejects gas from the galactic center, it cuts off its own fuel supply and eventually fades. Most large galaxies likely went through a quasar phase when they were younger. The Milky Way's central black hole, Sagittarius A*, is relatively quiet now, but probably shone as a quasar billions of years ago. Quasar spectra reveal the chemical history of the universe. By measuring the abundances of different elements in the gas around quasars, astronomers can determine how much stellar processing has occurred by that cosmic epoch. Early quasars show lower metallicities, indicating fewer generations of stars had lived and died. Later quasars show progressively higher metal content. This chemical evolution tells us how quickly the universe was enriched with heavy elements and helps constrain models of star formation history. The pattern of enrichment differs between the dense regions where galaxies cluster and the void regions where gas remains more pristine. The number density of quasars has declined dramatically since their peak epoch. Today, quasars are relatively rare, about 1 per billion cubic light years. At redshift 2 to 3, they were hundreds of times more common. This decline reflects the evolution of cosmic conditions. Gas reservoirs have been largely depleted, converted into stars, or ejected from galaxies. Galaxy mergers have become less frequent as the universe has expanded and structure formation has proceeded. The black holes that once powered quasars are still there at the centers of galaxies, but most lie dormant, accreting very little matter. Sagittarius A* accretes about 1 Earth mass per year, far too little to produce quasar-level luminosity. Gravitationally lensed quasars provide unique cosmological tests. When a massive galaxy or galaxy cluster lies between us and a distant quasar, the galaxy's gravity bends the quasar's light, often creating multiple images of the same quasar. Because the light paths have different lengths, variations in the quasar's brightness reach us at different times in each image. By measuring these time delays and modeling the lensing galaxy's mass distribution, astronomers can determine the Hubble constant, the universe's current expansion rate. This method is independent of other distance measurement techniques and provides an important cross-check on cosmological parameters. The scale of quasar-powered structures is staggering. Some quasars have created cavities in the intergalactic medium hundreds of thousands of light-years across, evacuated by the pressure of their jets and winds. These bubbles reveal the quasar's total energy output over millions of years. Radio observations show remnants of ancient jets extending far beyond their host galaxies, fossil evidence of past activity. These structures map the history of quasar activity and show how energy from supermassive black holes shapes the cosmic environment on scales far larger than the black holes themselves. Probing violent events through space-time ripples. For most of human history, astronomy meant observing electromagnetic radiation, visible light, infrared, radio waves, X-rays. But in 2015, the LIGO experiment detected gravitational waves for the first time, opening an entirely new window on the universe. Gravitational waves are ripples in space-time itself, produced when massive objects accelerate violently. They travel at the speed of light, stretching and squeezing space as they pass. The first detection came from two black holes, each about 30 solar masses, spiraling into each other and merging 1.3 billion light-years away. The collision released more energy in gravitational waves during its final fraction of a second than all the stars in the observable universe emit as light in the same time. The scale of spacetime distortion from gravitational waves is incredibly small. When LIGO detected that first merger, the gravitational waves stretched and squeezed space by less than 1/10,000th the diameter of a proton across LIGO's 4-kilometer arms. Detecting such minute changes required some of the most precise measurements ever achieved. LIGO's mirrors are positioned to better than a billionth of a centimeter, and the laser interferometry system can detect displacements smaller than the width of an atomic nucleus. This extreme precision allows LIGO to detect cataclysmic events occurring billions of light-years away, events that would be invisible with any form of telescope. Gravitational waves carry information electromagnetic radiation cannot provide. When black holes merge, they emit no light. Black holes, by definition, don't radiate. But their merger produces powerful gravitational waves encoding information about their masses, spins, and the final merged object. The frequency of gravitational waves increases as the black holes spiral closer, producing a characteristic chirp signal. The amplitude reveals how far away the merger occurred. The precise waveform depends on the black hole's properties, allowing astronomers to determine their masses and spins from the detected signal. This makes gravitational wave astronomy complementary to traditional electromagnetic observations. Neutron star mergers produce both gravitational waves and light, enabling multi-messenger astronomy. The 2017 detection of gravitational waves from merging neutron stars was followed within seconds by observations of a gamma-ray burst. Over the following days and weeks, telescopes across the world observed the event in visible light, infrared, radio waves, and X-rays. This multi-wavelength campaign revealed details impossible to obtain from gravitational waves alone. The production of heavy elements, the properties of the neutron star matter, and the rate at which the ejected material expanded. The combination of gravitational wave and electromagnetic observations provided a more complete picture than either could alone. The sources LIGO detects are at cosmological distances, often billions of light-years away. This makes gravitational waves a probe of the universe's structure and expansion. The gravitational wave signal carries information about the source's intrinsic properties, allowing astronomers to determine its distance without relying on the cosmic distance ladder. If the same event produces electromagnetic radiation, identifying the host galaxy provides a redshift measurement. Together, these measurements constrain the Hubble constant independently of other methods. As more gravitational wave sources are detected with electromagnetic counterparts, this approach will become an increasingly important cosmological tool. Future gravitational wave detectors will observe different frequency ranges, accessing different types of sources. LISA, a space-based detector planned for launch in the 2030s, will detect low-frequency gravitational waves from supermassive black hole mergers. These events, involving black holes millions to billions of times the Sun's mass, produce gravitational waves with periods of hours to days, far too low frequency for ground-based detectors. LISA will observe supermassive black hole mergers across most of cosmic history, revealing how these giants formed and grew. It will also detect thousands of compact binary systems in our own galaxy, creating a gravitational wave map of the Milky Way. Pulsar timing arrays offer another approach to gravitational wave detection. By precisely measuring the arrival times of radio pulses from millisecond pulses across the sky, astronomers can detect gravitational waves passing between the pulsars and Earth. These waves, with periods of years, come from supermassive black hole binaries throughout the universe. The combined signal from all these sources creates a gravitational wave background, analogous to the cosmic microwave background but in gravitational waves. Recent results from pulsar timing arrays suggest they're on the verge of detecting this background, which would reveal the population of supermassive black hole binaries across cosmic time. Gravitational waves also provide tests of general relativity in extreme conditions. The behavior of gravitational waves depends on the theory of gravity. Alternative theories predict different waveforms, different propagation speeds, or different polarization states. By comparing detected signals to predictions, physicists can test whether general relativity remains valid in the strong field regime near merging black holes. So far, all observations are consistent with general relativity's predictions, ruling out or constraining many alternative theories. The precision of these tests will improve as more events are detected and as detector sensitivity increases. The universe is full of gravitational wave sources we haven't yet detected. Core collapse supernovae should produce gravitational waves, though the signal depends on asymmetries in the collapse and is difficult to predict. Rapidly rotating neutron stars with surface irregularities should emit continuous gravitational waves. Binary white dwarf systems throughout the Milky Way create a gravitational wave foreground that future space-based detectors must account for. Even cosmic strings, hypothetical defects in spacetime from the early universe, would produce distinctive gravitational wave signatures. As detector networks expand and sensitivity improves, gravitational wave astronomy will reveal phenomena previously hidden from view. The detection of gravitational waves confirmed a century-old prediction and opened a new era in astronomy. Einstein predicted gravitational waves in 1916, but he doubted they'd ever be detected due to their weakness. For decades, their existence was debated. Indirect evidence came in the 1970s from observations of a binary pulsar system slowly losing energy at the exact rate gravitational wave emission predicts. But direct detection required extraordinary technological advances. The success of LIGO vindicated Einstein's theory and demonstrated that humanity can build instruments sensitive enough to detect spacetime ripples from events billions of light years away. This capability transforms our understanding of the universe's most violent phenomena. Cosmic acceleration and dark energy forces. About 68% of the universe's total energy density is something called dark energy. We don't know what it is. We can't see it, touch it, or detect it directly. We only know it exists because the universe's expansion is accelerating. In 1998, observations of distant type Ia supernovae revealed something shocking. These supernovae were fainter than expected for their redshifts, indicating they were farther away than cosmological models predicted. The only way to explain this was if the universe's expansion has been speeding up over the past 5 billion years. Something with negative pressure, something that pushes rather than pulls, must be driving this acceleration. We call it dark energy. Dark energy's properties are bizarre. Unlike matter and radiation, whose density decreases as the universe expands, dark energy's density remains constant. As space expands, new space appears, and dark energy fills this new space immediately, maintaining constant density. This means that while matter and radiation become more diluted over time, dark energy's total amount increases proportionally to volume. In the early universe, matter and radiation dominated, and gravity slowed the expansion. But as the universe expanded, matter density decreased while dark energy density stayed constant. About 5 billion years ago, dark energy began to dominate, and expansion started accelerating. The simplest explanation for dark energy is the cosmological constant, represented by the Greek letter lambda. Einstein originally introduced the cosmological constant in 1917 to create a static universe, balancing gravity's attractive force. When Hubble discovered the universe was expanding, Einstein reportedly called the cosmological constant his greatest blunder. But the cosmological constant returned in a different context. In quantum field theory, empty space isn't truly empty. It's filled with quantum fluctuations of virtual particles, popping in and out of existence. These fluctuations contribute energy to the vacuum, creating a constant energy density everywhere. This vacuum energy acts exactly like a cosmological constant, driving accelerated expansion. However, there's a severe problem. When physicists calculate the vacuum energy density from quantum field theory, they get a result about 10 to the power of 120 times larger than the dark energy density inferred from observations. This is perhaps the worst prediction in the history of physics, off by 120 orders of magnitude. Something must cancel most of the vacuum energy, leaving only the tiny amount we observe as dark energy. We have no idea what this cancellation mechanism might be. This is the cosmological constant problem, one of the deepest mysteries in fundamental physics. Alternative theories propose that dark energy isn't constant, but changes over time. Quintessence models introduce a new scalar field that pervades space, similar to the hypothetical inflaton field that drove cosmic inflation. This field's energy density varies slowly over time, affecting the expansion rate differently than a cosmological constant. Different quintessence models make different predictions about how dark energy evolves and how the universe's expansion history differs from models with a cosmological constant. So far, observations are consistent with constant dark energy, but uncertainties allow for slow evolution. Future surveys measuring the expansion history with greater precision will constrain these models. Dark energy's existence has profound implications for the universe's future. If dark energy remains constant, the universe will continue accelerating forever. Galaxies beyond our local gravitationally bound group will accelerate away from us, eventually crossing the cosmic horizon and disappearing from view. In about 100 billion years, all galaxies beyond the local group will have receded beyond observation. Their light will be redshifted into undetectability, and no new light from them will reach us. An observer in the far future will see a nearly empty universe, with only the merged remnant of the Milky Way and Andromeda visible against the darkness. If dark energy increases over time, a scenario called phantom energy, the fate is even more dramatic. Accelerating expansion would eventually overcome all gravitational binding, tearing apart galaxy clusters, then galaxies, then solar systems, then planets, then atoms themselves. This Big Rip scenario would end with the universe fragmenting into its most elementary constituents in a finite time, perhaps 100 billion years from now. Current observations don't favor this scenario, but they don't completely rule it out either. The universe's fate depends on dark energy's precise properties, which remain uncertain. Measuring dark energy's properties requires mapping the universe's expansion history across cosmic time. Multiple techniques contribute to this effort. Type Ia supernovae provide distance measurements across billions of years. Baryon acoustic oscillations, the characteristic scale imprinted by sound waves in the early universe, appear in galaxy distributions and provide a standard ruler. Galaxy cluster counts at different epochs reveal how structure formation has been affected by dark energy. Weak gravitational lensing of distant galaxies by foreground structure measures the growth of cosmic structure. Combining these measurements constrains how dark energy has evolved and tests whether it's truly constant. The discovery of dark energy earned the 2011 Nobel Prize in Physics, but it also highlighted how much we don't understand. In the late 1990s, cosmologists thought they understood the universe's composition: normal matter, dark matter, maybe some cosmological constant. The discovery that dark energy dominates the universe's energy budget was completely unexpected. It revealed that the universe's destiny is controlled by a component we know almost nothing about. We can measure dark energy's effects with increasing precision, but understanding what it actually is requires new physics beyond our current theories. Some physicists question whether dark energy exists at all. Perhaps our understanding of gravity is incomplete, and what we interpret as dark energy is really a modification of general relativity on cosmic scales. These modified gravity theories can reproduce the accelerated expansion without invoking new energy components. However, they face challenges explaining other observations, particularly gravitational wave propagation speeds and galaxy cluster dynamics. The 2017 neutron star merger observed in both gravitational waves and light constrained the speed of gravitational waves to match light speed to within 1 part in 10 to the power of 15, ruling out many modified gravity theories. Dark energy remains the simplest explanation consistent with all observations. Cosmic topology and repeating universes. If the universe is spatially infinite and contains a finite variety of matter configurations, then everything that can happen must happen infinitely many times. This isn't metaphysics, it's statistics applied to infinity. Consider a region of space 93 billion light-years across, the size of the observable universe. It contains about 10 to the power of 80 atoms. The number of possible arrangements of these atoms is enormous, but finite. In a truly infinite universe, every one of these arrangements must appear somewhere. That means there are infinite regions identical to our observable universe scattered throughout infinity, complete with identical copies of Earth, you, and this moment. The logic is inescapable if the universe is infinite. With finite configurations and infinite space, repetition is guaranteed. How far would you need to travel to reach an identical region? The answer depends on how many configurations are possible. Estimates suggest that an exact duplicate of the observable universe should exist about 10 to the power of 10 to the power of 29 meters away. This number is so large it has no physical meaning. It's vastly larger than the observable universe itself. But in an infinite space, such distances must exist somewhere. There are infinite copies scattered throughout, each one identical down to every quantum state, each one experiencing this exact moment simultaneously. But it gets stranger. Between exact copies, there are near copies with small differences. A universe identical to ours except one electron is in a slightly different position. A universe identical except you made a different choice at breakfast. The number of near copies vastly exceeds the number of exact copies. Within the infinite universe, there are infinite versions of you living out every possible variation of your life. Some versions differ so slightly you'd never notice. Others diverge dramatically at key decision points. In the ensemble of infinite copies, every quantum possibility that could have happened did happen somewhere. This bothers some physicists enough that they question whether the universe really is infinite. If it's merely very large, but finite, then these disturbing implications disappear. There would be only one you, one Earth, one history. The lack of infinite repetition makes probability meaningful in a way it isn't in an infinite universe. But current observations suggest the universe is either infinite or so large that the distinction is irrelevant. The universe's spatial geometry appears flat to within measurement errors, and a flat universe is likely infinite. If there's any spatial curvature, it's so slight that the total universe is many orders of magnitude larger than the observable portion. Eternal inflation compounds these issues. If inflation is eternal, spawning infinite bubble universes, then not only do infinite copies exist within each bubble, but there are infinitely many bubbles. The multiverse of eternal inflation contains infinite instances of every possible bubble universe, including infinite bubbles identical to ours, and infinite bubbles with different physical laws. The level of repetition becomes layered. Infinite copies within each bubble, infinite bubbles with the same properties, infinite variations of bubbles with different properties. The mathematical structure is baroque beyond comprehension. Some argue this makes the multiverse untestable and therefore unscientific. If everything possible happens infinitely many times, how can we make predictions or test theories? What does probability mean in an infinite ensemble where every outcome occurs infinitely? These are legitimate philosophical concerns, and physicists debate them vigorously. Anthropic reasoning, the idea that we observe particular conditions because they're necessary for observers to exist, becomes important in an infinite multiverse. We find ourselves in a universe with the right properties for life, not because those properties are universal, but because we couldn't exist in universes with different properties. The selection effect explains our observations without requiring fine-tuning. But anthropic reasoning is controversial. It feels like giving up on finding fundamental explanations for why the universe has the properties it does. Instead of seeking a theory that predicts specific values for physical constants, anthropic reasoning says those constants vary across the multiverse, and we happen to be in a region where they allow life. This approach is scientifically productive only if it makes testable predictions. Some argue it does. Anthropic reasoning can predict the approximate value of the cosmological constant by considering what range of values allows galaxy formation. The prediction roughly matches observations, though whether this constitutes a genuine success or post hoc reasoning remains debated. The observable universe may be all we ever directly access, but that doesn't mean the rest is irrelevant. Cosmic inflation's predictions about the observable universe's properties depend on assumptions about inflation's overall structure, including whether it's eternal. The distribution of cosmic microwave background fluctuations, the universe's spatial geometry, even the possibility of detecting primordial gravitational waves all connect to questions about the universe's total size and structure. Understanding the observable part requires theorizing about the whole, even if the whole is unobservable. Living in a possibly infinite universe with infinite copies of yourself is conceptually unsettling. It challenges notions of uniqueness and identity, but it's a consequence of taking seriously our best current theories and observations. The universe appears flat, suggesting it's infinite. Inflation appears to have occurred, potentially eternally. These aren't certainties, but they're where the evidence points. As uncomfortable as infinite repetition might be philosophically, science follows the evidence regardless of comfort. The universe may be stranger than we imagine, and strangeness shouldn't disqualify ideas that fit observations and follow logically from well-tested theories. Ultimately, questions about the universe's total size and structure might remain permanently unanswerable. We can only observe the finite bubble of space from which light has reached us. We can theorize about what lies beyond based on extrapolating from what we see, but direct verification is impossible. This is the ultimate limit of observational cosmology. We're confined to one observable patch of a possibly infinite whole. We can infer, we can reason, we can construct theories, but we can never see for ourselves. The universe keeps its largest secrets beyond our observational horizon, forever out of reach.